The Big Bang isn't just the start of the universe, it might be the start of time itself. The moment before stops making sense, and yet our equations keep whispering that the universe could have come from nothing. So what does physics mean by nothing? And if time had a beginning, what, if anything, could exist before it? Imagine erasing every star, every atom, every photon, then erasing the stage they ever appeared upon. What remains is not silence, but a question sharp enough to bend reason. In this film, we follow that question to the places where physics stops sounding like common sense and starts sounding like a confession. We will treat nothing as scientists must, not as a mood or metaphor, but as a claim with measurable consequences. Because the universe does not offer us a single void, it offers a hierarchy of emptiness, each rung stranger than the last. First comes the everyday vacancy, space cleared of matter, a dark room with the lights off and the air removed. Then comes a quieter, more disciplined absence, the quantum vacuum where fields remain, and the lowest energy still refuses to sit perfectly still. In that domain, empty can press on metal plates, shift atomic colours, and leave traces in the numbers we measure to absurd precision. Nothingness begins to look less like a blank page and more like a tightly written margin. But even that may be too generous, because the vacuum presumes a background where distances, durations, and causality already have meaning. Push deeper, and the very idea of a smooth space-time starts to fray. Geometry becomes restless, and the familiar distinction between where and when can blur. At the frontiers, researchers speak carefully about quantum gravity, not as a single theory, but as a demand forced on us by the limits of our best ones. Along the way, we will meet the disciplined evidence that anchors cosmology to reality. Redshifts mapped across the sky, the cold afterglow of the cosmic microwave background, and the light elements forged when the universe was young. These are not philosophical ornaments. They are forensic marks left on the scene, and they constrain what any story about origins is allowed to say. They also reveal why the simplest extrapolations end in a warning sign, a point where classical equations insist on infinities and quietly admit defeat. Then comes a more unsettling possibility, that the earliest chapters of cosmic history were not merely hot, but accelerated, an expansion so swift it could smooth, stretch, and seed the universe we observe now. If that happened, it did not erase the question of nothing, it sharpened it, because it ties the largest structures in the sky to the smallest fluctuations permitted by quantum rules. It also raises a delicate issue about beginnings that we cannot settle with rhetoric, only with signatures hidden in patterns. We will keep returning to a single discipline throughout this journey, distinguishing what a word suggests from what a theory means. Nothing in physics can be an empty region, a vacuum state, a lack of classical space-time, or an ideal of total absence that may lie beyond any model. Each step down that ladder removes familiar supports, and each removal changes what counts as an explanation. At the lowest rungs, even the status of laws becomes a live question, because a law that describes the universe still assumes a framework in which describing is possible. This is not a hunt for a slogan, or for a comforting end to curiosity. It is an exploration of what our best ideas can legitimately claim, what they merely suggest, and what they forbid us to say. The stakes are high because the question is not only where the universe came from, it is whether the notion of coming from anywhere applies at all. And yet, despite the austere logic, the universe is not stingy with clues. It leaves faint imprints in microwave light, in the distribution of galaxies, in the abundance of helium, and perhaps one day in primordial gravitational waves that would pass through us like a memory. If we listen with enough care, those traces can tell us whether the early cosmos was a boundary, a transition, a bounce, or a local event inside a much larger reality. So we begin with a simple promise. We will not use nothing as a punchline. We will test it, refine it, and watch it change shape as we move from language to measurement, from emptiness to vacuum, from vacuum to geometry, and from geometry to the edge where time itself may become optional. What we find there will not be a final answer, but it may be the clearest view we have ever earned of the universe's first conditions, and of the strange generosity with which reality lets us know anything at all. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We will start where the word before breaks, descend into the quantum vacuum, and climb back towards spacetime's limits with inflation and quantum gravity. At the end, we will ask what future observations might still reveal, without assuming the universe owes us closure. We begin at the edge where language stops matching the universe, and the familiar words start to wobble. We ask a question that sounds simple, then turns unstable in our hands. How did nothing exist before the Big Bang? The phrase is familiar, but every word carries hidden assumptions that quietly shape the picture in our minds. It assumes a time called before, as if a clock were already running somewhere beyond the cosmos. It assumes a state called nothing, as if emptiness were a clean, featureless condition. It assumes the Big Bang was an event inside a larger stage, like a spark inside a room. Cosmology starts by correcting the picture that most minds reach for, because intuition is trained on everyday motion. The Big Bang was not a bomb going off in empty space, with debris flying outward from a center. It was the rapid expansion of space itself, with matter and radiation already inside, hot, dense, and tightly coupled. Expansion here does not mean galaxies moving through a pre-existing void like shrapnel through air. It means the metric that measures distance is changing with time, and that change is part of space-time's geometry. The universe is not expanding into something, because the theory does not require an outside. The distances within the universe are increasing, even when nothing locally moves in the ordinary sense. That distinction removes a cluster of common misconceptions, and it does so with surprising force. There is no central point where the Big Bang happened, no privileged location marked by a cosmic scar. There is no outer edge where a blast front is racing outward into darkness. Every region sees other regions receding because the space between them stretches, uniformly, on large scales. We can say this without pretending it feels intuitive, because it rarely does on first contact. Our brains evolved for objects moving in space, not for space itself changing under the objects. Yet the mathematics of general relativity makes this idea precise, and it does not treat it as metaphor. Space-time is not a passive container. It is part of the physical system, responding to energy and momentum. In Einstein's equations, geometry and content are locked together in a mutual negotiation. Matter and radiation tell space-time how to curve, and curved space-time tells matter how to move. When we describe the universe expanding, we are describing a solution to those equations, not a cinematic effect. Even the word distance becomes time-dependent, because the ruler is built into the geometry. So the first rule of this documentary is simple, and we will return to it whenever the imagery gets too loud. When we say Big Bang, we mean a hot, dense, early state followed by expansion and cooling. We do not mean a fireball exploding into darkness, leaving a hollow center behind. The second rule is harder, and it targets the word before, which behaves like a trap. In general relativity, time is not an external clock that ticks independently of the universe. Time is one coordinate of space-time tied to gravity, motion, and the way observers slice the cosmos into nows. If space-time has a beginning, time may not extend past it. This is where the question becomes dangerously ambiguous, even if it sounds grammatically correct. Before can mean earlier than an event within time, like before sunrise or before a heartbeat. It can also mean outside the entire timeline, as if time were embedded in a larger time. Physics does not grant that second meaning for free, and it does not promise a place to stand outside the system. When people ask what happened before the Big Bang, they often picture a moment earlier than the first moment. That picture assumes a background time that keeps ticking, even if the universe is absent. But if the Big Bang marks the start of space-time, there may be no earlier moment to point to, no coordinate to label, no physical process to anchor it. Undefined is not the same as unknown, and that difference matters more than it first appears. Unknown means there is a fact, and we lack access to it, like a hidden planet behind a star. Undefined means the question fails to map onto the theory's concepts, even in principle. Asking what is north of the North Pole is not answered by better instruments, because the coordinate system ends. Cosmologists do not say this to dodge curiosity, or to hide behind technicalities. They say it because the equations connect time to the geometry of the universe, and geometry can have boundaries. If the geometry reaches a boundary, the time coordinate can end there, not as a dramatic explosion, but but as a limit of description. The word before breaks because it expects time to continue, as if continuation were guaranteed by grammar. Still, the Big Bang model is not a philosophical preference. It is a scientific framework built from observations, sharpened by prediction, and corrected by data when it drifts. It earns its authority by explaining multiple lines of evidence with one coherent story, and by surviving tests that could have broken it. The first pillar is expansion, measured in the sky with patient, decades-long work. In the 1910s and 1920s, Vesto Slipher measured galaxy spectra and found striking redshifts, even before the full interpretation was clear. Edwin Hubble then used Cepheid variable stars to estimate distances, showing that many nebulae were separate galaxies far beyond the Milky Way. Georges Lemaitre, working from Einstein's equations, connected those distances and redshifts into a dynamical universe. Farther galaxies show larger redshifts, which we interpret as cosmic expansion rather than a simple spray of velocities. Redshift is not just a Doppler effect from motion through space, although Doppler intuition can be a helpful stepping stone. In an expanding universe, light stretches as space stretches, and the wavelength lengthens along the journey. Spectral lines slide toward red, not because the source flies away through a static void, but because the metric itself evolves. The relationship between distance and redshift becomes a fingerprint of an expanding geometry, and it can be measured in multiple independent ways. Astronomers build a distance ladder using standard candles and standard rulers, cross-checking methods to reduce systematic error. The result is not a single number, but a consistent pattern. The universe is expanding, and it has been doing so for billions of years. When we say the cosmos has a history, this is one of the reasons we're allowed to say it. Run that expansion backward in time, and the universe becomes denser and hotter, not in one location, but everywhere at once. Galaxies crowd together, radiation intensifies, and the early universe approaches a plasma state where atoms cannot hold together. This is not a guess about a single point in space, like rewinding an explosion to its origin. It is a statement about the whole space-time history implied by the equations and the data. The second pillar is the cosmic microwave background, a signal so quiet it could have been dismissed as noise. In 1965, Arno Penzias and Robert Wilson found a persistent microwave hiss from every direction, even after they cleaned their antenna and chased every mundane explanation. It matched a prediction made decades earlier by Ralph Alpher and Robert Herman, who argued that a hot early universe would leave behind relic radiation. The universe, in effect, should still glow, just at a temperature chilled by expansion. The CMB is not light from a distant object like a galaxy or a star, and that difference is crucial. It is the afterglow of the time when the universe cooled enough for electrons and nuclei to form neutral atoms, a process called recombination. Before that, the universe was an opaque plasma where photons scattered constantly off free electrons. After that, photons travelled freely, and the universe became transparent, an event sometimes called the surface of last scattering. Those photons have been stretched by expansion for billions of years, their energies diluted as the cosmic scale factor grew. Their temperature today is about 2.7 Kelvin, almost uniform across the sky, as if space itself carries a faint thermal memory. Tiny fluctuations remain at the level of tens of microkelvin, and they are not random decoration. They encode the seeds of later structure, slight over and under densities that gravity could amplify into galaxies and clusters. When satellites map those fluctuations, the visuals look like a mottled, ancient weather map of the infant cosmos. Patterns in the CMB power spectrum reveal the universe's composition and geometry, including the balance of ordinary matter, and dark energy. Even if we avoid the deeper parameter story in this chapter, the core point stands clearly. The CMB makes the early hot universe hard to deny, because it is a relic that fills all directions. The third pillar is primordial nucleosynthesis, which turns the early universe into a nuclear laboratory. In the first minutes, the universe was hot enough for nuclear reactions, but it was also expanding and cooling rapidly. Protons and neutrons collided, fused, and fell out of equilibrium as temperatures dropped. The theory predicts specific abundances of hydrogen, helium, and traces of deuterium and lithium, and those predictions depend sensitively on conditions in that early window. A key detail is timing, because the universe did not stay hot long enough to build heavy elements. After a few minutes, densities fell and fusion effectively shut down, leaving a cosmos dominated by hydrogen and helium. That is why carbon, oxygen, and iron are not primordial in large amounts, and why stars must later manufacture them. The early universe sets the baseline, and stellar evolution writes the later chapters. When astronomers measure ancient gas clouds and old stars, the numbers line up with remarkable consistency. About 3/4 hydrogen by mass, about 1/4 helium, with small but meaningful amounts of deuterium that act like a sensitive cosmic thermometer. Lithium is more complicated, and the mismatch is a clue, not a collapse, because it points to either astrophysical processing or subtle gaps in modelling. The overall agreement is striking, and it ties chemistry to cosmology. These three pillars do not prove every detail of the earliest instant, and they do not pretend to. They establish a robust timeline from a hot, dense beginning to the cosmos we see, and they do it with independent evidence. Expansion, relic radiation, and light element abundances converge on the same basic picture, like three shadows cast by one object. When different measurements agree, the confidence is earned rather than declared. Yet the story contains a warning sign at its beginning, a place where the mathematics grow sharp and uncomfortable. When we extrapolate the equations of general relativity backward, densities and curvatures can blow up. The math points to a singularity, a place where quantities become infinite and the classical description stops making sense. In physics, infinities are usually not a triumph, even when they look dramatic on a chalkboard. They are a signpost that a theory has been pushed beyond its domain, like using fluid equations to describe individual molecules. A singularity in the equations does not necessarily mean nature contains a literal point of infinite density. It often means our description has run out, and the next layer of physics has not yet been written into the model. The Big Bang singularity, in this sense, is not an observed object sitting at the bottom of time. It is an inference from extending a classical theory too far past the regime where quantum effects should dominate. General relativity works exquisitely for planets, stars, and galaxies, and it even predicts black holes with astonishing accuracy. But it is not a quantum theory, and the early universe demands quantum gravity, where space-time itself may have discrete or probabilistic structure. So we hold two truths at once, and we resist the urge to collapse them into a slogan. The Big Bang model is strongly supported for much of cosmic history, from nucleosynthesis onward through the formation of structure. But the earliest moments are a frontier where known physics fails, and that failure is informative rather than embarrassing. That boundary is where our question about before becomes both tempting and treacherous, because it presses directly on the edge of our map. At this boundary, the word nothing also starts to change shape, and the change is not merely philosophical. In everyday speech, nothing means empty space, no matter, no light, no events, and no lingering traces. In physics, empty space is not always empty, even when it looks perfectly dark. Fields can exist without particles, and the vacuum can carry energy, fluctuations, and constraints that show up in experiments. But we are not ready to define nothing yet, because the word before must be handled first. We need to see why the urge to imagine a prior state is so persistent, even among people who accept the evidence. Human intuition treats time as a line that must extend in both directions, because our experience contains no true beginning. A beginning feels like a missing cause, and the mind reaches for a hidden prelude. Science has trained us to look for earlier explanations, and that training is one of its great strengths. We ask what made the star ignite, what formed the galaxy, what set the initial conditions of a chemical reaction. The Big Bang seems to demand the same treatment, because it sounds like an event with a trigger. If everything expanded from a hot, dense state, what set that state, and why did it have those properties? General relativity answers with a challenge that is easy to say and hard to absorb. It says the geometry of space-time is dynamical, and time itself is part of what evolves, not a stagehand off-screen. If time begins, the demand for an earlier cause may be misplaced, because causation is a relation within time. Causes precede effects along time-like paths, and those paths require a space-time in which precede is defined. This does not mean the universe is beyond explanation, and it does not license mysticism. It means the form of explanation may change, shifting from earlier moments to deeper laws. We might replace a question about what happened earlier with a question about what principles constrain the whole history. We might seek a theory where the beginning is not a singular point, but a transition between regimes of description. Some possibilities already exist in the scientific imagination, and they hover at the edge of this chapter like silhouettes. Inflation proposes a brief era of accelerated expansion that can smooth and flatten the universe, making distant regions look unexpectedly uniform. Quantum cosmology explores whether spacetime can emerge from quantum conditions, where classical time is not fundamental. Bouncing models ask if a contraction preceded expansion, turning before into a different kind of chapter break. Each option rewrites what before could mean, and each must answer to evidence. But in this opening chapter, we stay disciplined, because discipline is what keeps mystery from becoming fog. We do not jump to solutions before we understand the problem, and we do not treat speculation as a substitute for clarity. The problem is that our words smuggle in a background stage. Big Bang as explosion, before as earlier time, nothing as simple absence. Once those images are inside the mind, they keep generating questions that may not fit the physics. We replace those pictures with the minimal testable core, and we let that core do its quiet work. The universe has been expanding from a hotter, denser state, and the evidence is written in redshifts, in microwave photons, and in the chemistry of the light elements. This framework works astonishingly well until it approaches a regime where classical spacetime breaks. At that break, the story does not end, but the vocabulary must be renegotiated. That break is not a failure of curiosity, it is the exact place where curiosity becomes scientific. If the singularity marks a limit, then the next question is what theory replaces it, and what new predictions follow. If before is undefined in classical spacetime, then we ask whether a deeper theory restores meaning, or whether it replaces the question with a better one. What would count as an answer, and what would count as a category mistake? The emotional tension of this documentary lives here, in the gap between what we can picture and what we can justify. We are searching for a concept of nothing that can survive contact with physics, not just with poetry. We are also searching for a concept of origin that does not collapse into wordplay, even when the mathematics becomes abstract. The universe does not owe us an intuitive beginning, but it may offer a coherent one. We end this chapter with a rule for the journey ahead, and it is meant to keep us honest. We will treat the Big Bang as a boundary of our current description, not a definitive first frame. We will treat before as a term that must be earned by theory, not assumed by grammar. When a word breaks, we will not force it to work. We will ask what the universe is telling us instead. Next, we turn to the other unstable word in our opening question. If before is problematic, then nothing becomes the real battleground. We step into modern physics to ask what the vacuum is, what it contains, and whether nothing can ever be truly nothing. Chapter 1 left us with a boundary where before may fail inside our best spacetime story, because time itself seems braided into the universe's expansion. Now we test the other unstable word in the question. Physics has a candidate for nothing that is not a void. It is the quantum vacuum, the lowest energy state of fields that fill the universe. To reach it, we step down from galaxies and expansion into the framework beneath matter itself, where the familiar world starts to look like a set of rules. The camera that once lingered on clusters and filaments now dives inward, past stars and atoms, toward a quieter stage where stuff becomes a pattern. We pass the bright haze of nebulae, then the hard glint of metal, then the soft blur of molecular motion, until the picture becomes abstract. Modern physics does not treat particles as tiny beads moving through emptiness. It treats them as excitations, localized ripples, of underlying quantum fields. In quantum field theory, every species of particle corresponds to a field defined at every point in space and time, even where no particle is present. The electron is not a separate substance from the electron field, and it is not a marble riding a track. It is a quantized disturbance of that field, carrying a fixed charge and mass because the field's symmetries demand it. A photon is a quantized excitation of the electromagnetic field, a packet of energy and momentum tied to the field's oscillation. This shift matters because it changes what empty space can mean, and it changes it in a way that is mathematically unavoidable. If fields are fundamental, then space without particles is not space without fields, because the fields are the thing that can be excited. The vacuum is not a blank container waiting to be filled. It is a particular state of the fields, defined by symmetries, interactions, and a minimum energy consistent with quantum rules. In everyday language, vacuum means absence, like an evacuated chamber with air removed and pumps still humming outside the glass. In quantum field theory, vacuum means ground state, and that phrase is doing real work. It is the state with no real particles present as defined by the field's particle concept for a given observer and background. That definition is already a warning that vacuum is technical, not philosophical. The quantum vacuum is nothing, only in a narrow sense, and it is narrow in a way the equations keep reminding us. It is the lowest energy configuration, not the absence of the system. The system still includes fields, their commutation relations, their couplings, and the space-time they live on. Even before we discuss fluctuations, the vacuum already presumes a stage and rules. Historically, this is a sharp reversal from older intuitions about emptiness, and it echoes a long argument in natural philosophy. Classical physics could imagine a perfect void, a region with no matter and no forces, where nothing at all happens. The 19th century even flirted with an ether, a material-like medium for light, and then discarded it after relativity. Quantum field theory keeps the medium-like idea in a new form, but it is not a substance you can scoop. It is a set of fields whose values and correlations exist even when no particles are present. The next surprise is that the ground state is not perfectly still, even when you have removed every real particle you can. Quantum mechanics blocks the classical idea of complete rest, because it replaces certainty with a structured kind of spread. The uncertainty principle says certain pairs of quantities cannot both be sharply fixed, even in the lowest energy state. For a field, the relevant quantities behave like position and momentum for each mode of oscillation. A useful picture is that each field mode resembles a quantum harmonic oscillator, and the analogy is more than poetic. Visually, imagine a vast orchestra of independent springs, one for each wavelength and direction, each capable of vibrating. Classically, the lowest energy would be zero, with no motion at all, and the springs would sit dead still. Quantum mechanically, the lowest state still has 0-point energy, a minimum jitter built into the mathematics. The field cannot have both exactly zero amplitude and exactly zero rate of change, because those variables are linked by the theory's commutators. If you squeeze the uncertainty in one, the other must spread out, and the ground state is the compromise. This is not a statement about experimental clumsiness or hidden vibrations we failed to damp. It is a statement about what the theory allows as a state of definite energy. This is where the phrase vacuum fluctuations enters, and it is easy to misunderstand because the word fluctuation sounds like a visible commotion. Fluctuation does not mean the vacuum is a frothing sea of particles popping in and out like fireworks. It means the vacuum state has irreducible quantum variance in measurable quantities, even when averages look calm. The field's value and its conjugate momentum cannot both be fixed with certainty. If we could draw the vacuum, we would not show it as a storm of objects, because objects are the wrong visual grammar. We would show it as a calm surface with fine-grained texture, correlations that appear only when you measure carefully. In quantum language, the vacuum is a highly structured state with entanglement between regions of space. Even when the average field value is zero, the spread around that average is not. That entanglement has a practical meaning, not just a mystical one, because it tells you what measurements in one region imply about another. If you carve space into two halves, the vacuum does not factor into two independent states. The correlations are subtle, and they hide until you ask the right question with the right apparatus. The vacuum is quiet, but it is not simple. In calculations, we often describe these variances using virtual processes, and the language can be treacherous if taken too literally. Virtual particles are not particles you can detect directly with a counter, and they are not little beads that briefly exist in the lab. They are internal lines in perturbation theory, bookkeeping devices that encode how fields interact. They summarize how one field disturbance influences another through intermediate states. The borrowing energy story is a metaphor that can mislead, because it sounds like a loophole in conservation laws. Energy conservation is not casually violated in real measurements, and no experiment has ever watched energy appear from nowhere and remain. The uncertainty principle does not grant a license for free energy extraction. It constrains simultaneous knowledge and sets limits on how sharply a state can be defined. What the vacuum can do is influence probabilities and shift energy levels in systems coupled to fields, and those shifts are where the physics becomes testable. It can modify forces between objects by changing which field modes are allowed. It can renormalize parameters, like charge and mass, through interactions with quantum fluctuations. These effects are subtle, but they are measurable. Renormalization sounds like a mathematical trick, yet it reflects a physical idea about scale and what you count as part of the object. When you probe an electron at different distances, you effectively include different layers of vacuum polarization around it. The bare parameters in the equations are not what the laboratory measures directly. What we measure is the dressed effective behavior after the vacuum has done its quiet work. So the vacuum is not emptiness in the everyday sense, and it is not merely a philosophical placeholder. It is a physical state with structure, even when it contains no real particles. The question becomes whether this structure leaves fingerprints that experiments can read. Physics answers yes, and it answers with several independent lines of evidence. One of the clearest demonstrations is the Casimir effect, which turns geometry into a force you can weigh. Place two uncharged, conducting plates very close together in a vacuum and align them so their faces are parallel. The gap can be micrometers or less, a distance where the ordinary air molecules are removed and stray charges must be controlled. Quantum fields between the plates must satisfy boundary conditions, allowing only certain modes. Outside the plates, more modes are available. That difference in allowed vacuum modes changes the vacuum energy density between the plates relative to outside, and the imbalance shows up as a macroscopic push. The result is a net force pushing the plates together, as if the outside vacuum has more ways to fluctuate. The force is tiny, but it has been measured with increasing precision, using torsion balances and microfabricated cantilevers. It is not a chemical glue or a stray electrostatic trick when experiments are carefully controlled. The Casimir effect is often presented as vacuum pressure, but the deeper point is constraint, because the vacuum depends on what the world allows. The vacuum state depends on the physical setup, including geometry, materials, and separation. Change the boundaries, and you change the spectrum of fluctuations. The vacuum responds, and the response can push on matter. If we linger on the visuals, the plates look like two dark mirrors in a clean, silent chamber, held steady by delicate mounts. Between them, only certain wavelengths fit, like notes allowed on a shortened string. Outside, the field has a broader range of notes, and the imbalance becomes a mechanical nudge. The vacuum, which was supposed to be nothing, behaves like an environment with rules. Another window into vacuum physics is the Lamb shift, which reveals the vacuum's influence inside the simplest atom. In the hydrogen atom, certain energy levels that should match in a simple Dirac picture are slightly split. The electron interacts with the quantized electromagnetic field, including vacuum fluctuations. Those interactions shift the energy levels in a way that matches quantum electrodynamics. The historical arc matters here, because this was not a small footnote hidden in the decimals of a table. In the 1940s, precision spectroscopy revealed a discrepancy that the simplest relativistic theory of the electron could not explain. The Lamb shift helped drive the development of modern quantum electrodynamics, including the systematic handling of infinities through renormalization. It was a case where empty space corrected the atom's internal bookkeeping. The Lamb shift is not a philosophical argument about emptiness, and it does not rely on interpretive gestures. It is a numerical correction that shows up in spectroscopy, a tiny change in frequency that can be measured and compared. It helped confirm that the electromagnetic field must be quantized. It also showed that empty space participates in atomic structure through the field's ground state. A related effect is the electron's anomalous magnetic moment, which is a precision test of the same underlying idea. The electron's magnetic behavior deviates slightly from the simplest prediction, and the deviation is not an experimental accident. That deviation arises from quantum corrections involving the vacuum and interactions, including loops in the theory's diagrams. The agreement between theory and experiment is among the most precise in all science. Taken together, these examples build a single message, and the message is sturdier because it comes from different kinds of measurements. The vacuum is not a mere absence of matter, and it is not just a convenient reference point. It is a state of quantum fields that can influence forces and energies. If you change the environment, you change the vacuum's allowed fluctuations, and you can measure the difference. At this point, nothing has already climbed down one rung on the ladder of absences, and it has not reached the bottom. We removed particles, but we did not remove fields. We removed classical stillness, but we did not remove quantum variance. The vacuum is a kind of minimal something, defined by the theory that describes the world. Yet cosmology forces the issue further, because the vacuum is not only a laboratory curiosity under polished steel and careful shielding. If the vacuum carries energy, then it gravitates, and gravity does not ignore baselines. In general relativity, energy and pressure contribute to space-time curvature. A vacuum energy that is uniform in space acts like a cosmological constant, a term that behaves the same everywhere. This connects the quantum vacuum to the largest mystery in the sky, where the evidence arrives as faint light and careful statistics. Observations of distant supernovae, the cosmic microwave background, and large-scale structure indicate that the expansion of the universe is accelerating. The simplest explanation is dark energy, a smooth component with negative pressure. Mathematically, a cosmological constant fits the data remarkably well. A cosmological constant looks like an energy density of empty space, and the resemblance is too close to ignore for long. That sounds like vacuum energy, so the temptation is immediate and almost irresistible. Maybe the vacuum is not only not empty, maybe it is the dominant energy component of the universe today, quietly steering cosmic geometry. But when we try to compute vacuum energy in quantum field theory, the numbers become disturbing. In quantum field theory, each mode contributes a 0-point energy, and the list of modes is vast beyond intuition. If you list the modes by wavelength, you find infinitely many, extending to arbitrarily short scales. Summed over all modes, the naive result diverges, as if the vacuum energy is infinite. Renormalization tells us that only energy differences often matter in non-gravitational settings. But gravity couples to absolute energy density, at least in the way the equations are written. That makes the vacuum energy hard to ignore because space-time responds to whatever energy is present, even if it is uniform. In the lab, we can subtract a constant energy and nothing changes, because only differences affect forces. In cosmology, a constant energy density changes the expansion rate of the universe itself. The vacuum, if it truly has an energy density, becomes a source term in Einstein's equations. If we impose a cutoff at a high energy scale, like the Planck scale where quantum gravity becomes important, the estimated vacuum energy density is enormous. It is many orders of magnitude larger than the dark energy density inferred from cosmology. The mismatch is not a factor of 2 or a factor of 1,000. It is a catastrophic gap, often quoted as the worst prediction in physics. This is the cosmological constant problem, and the wording matters because it is easy to aim at the wrong target. The problem is not simply that we cannot calculate a number. The problem is that natural-looking estimates are wildly inconsistent with a universe that lasts billions of years and forms galaxies. Why is the observed vacuum energy so small compared to naive quantum expectations? Why does it not curve space-time violently and prevent the universe we see? If the vacuum is physical, it should gravitate, and yet its gravitational effect is strangely mild, like a whisper where a shout was expected. The sky looks calm on the larger scales, with expansion that accelerates gently rather than tearing everything apart. That calmness, in the face of quantum expectations, feels like a clue. It suggests either a deep cancellation or a missing principle. Several responses exist, and none is fully satisfying, which is why the mystery survives in textbooks and seminars. One possibility is that the vacuum energy contributions cancel almost perfectly due to a symmetry we do not yet understand. Supersymmetry would cancel bosonic and fermionic contributions, because their 0-point energies come with opposite signs. But supersymmetry must be broken in our world, and the remaining energy is still too large. Another possibility is that our calculation is wrong because we are missing quantum gravity, the piece that should tell us what mode even means at extreme scales. Perhaps the very idea of summing field modes up to the Planck scale is misguided. Perhaps space-time itself has a discrete microstructure that changes what counts as a mode. Or perhaps vacuum energy is not an independent thing at all, but an emergent bookkeeping term that only appears in an effective description. Another possibility is that the cosmological constant is not vacuum energy at all, even if the equations look similar. Dark energy could be a dynamical field, like quintessence, slowly evolving over cosmic time. In that case, the energy density would change, and the pressure would not be exactly constant. Or it could be an emergent effect of space-time microphysics, a large-scale residue of deeper degrees of freedom. But the simplest fit to data still resembles a constant, which keeps vacuum energy in the conversation. This tension is productive because it shows the limits of our current nothing, and it marks where our language outruns our theory. The quantum vacuum is not a final answer to origins. It is a state defined within a theory that already assumes fields and spacetime. When we try to connect it to gravity, we expose a deep mismatch between quantum expectations and cosmic measurements, so we should be careful about a common rhetorical leap, because it slides past the very definitions we have worked to sharpen. People sometimes say the universe could come from nothing, because quantum fluctuations can create particles. But the quantum vacuum is not nothing in the absolute sense. It is a structured state governed by laws, defined on a background, with degrees of freedom that can fluctuate. Even the phrase "create particles" needs context, because particle number is not always a fixed observer-independent concept, and the vacuum is not a single universal emptiness. In curved spacetime or accelerating frames, what counts as a particle can change. Effects like Unruh radiation and Hawking radiation show that vacuum depends on the observer and the geometry. The vacuum is relational, tied to how you define energy. For an accelerating observer, the ordinary vacuum can look warm, filled with a thermal bath that was not there for an inertial observer. For an observer far from a black hole, the vacuum near the horizon can look like it is producing radiation. The field is the same, but the slicing of spacetime into time and space changes what counts as a particle. The vacuum in this sense is relational, tied to how you define energy. That observer dependence matters for cosmology, where the background is not static and the geometry itself evolves. The early universe is not a quiet stage with one preferred time, and its geometry changes rapidly. As spacetime expands, the notion of vacuum can evolve because the definition of positive and negative frequency modes can shift. Quantum fields in an expanding background can be excited, and those excitations concede structure. Inflationary cosmology uses this idea, turning vacuum fluctuations into the primordial density perturbations that later become galaxies, clusters, and the web-like pattern we began with. The story is visually striking when you translate it into images, because it makes the small become immense. Tiny quantum variations, initially microscopic, are stretched by rapid expansion until they span astronomical distances. What began as uncertainty in a field becomes a faint pattern imprinted across the sky. In that story, the vacuum is again active, but not magical, and the mechanism has a clear chain of steps. The fluctuations are stretched by expansion and become classical-looking perturbations because their phases decohere and their correlations freeze. Their statistical pattern can be predicted and compared with the cosmic microwave background. The success of this framework is one reason vacuum physics is central to modern cosmology. But even here, we must separate two claims that sound similar when spoken quickly, because one is physics and the other is a slogan. Vacuum fluctuations can become real excitations in a changing background, and that is a well-defined process in quantum field theory. That does not mean the universe came from absolute nothing. It means that given us space-time and quantum fields, the lowest energy state is not featureless, and dynamics can amplify its fluctuations. So the chapter's core distinction becomes sharp, and it sharpens the moment you ask what has been assumed. Philosophical nothing is the absence of anything at all, including laws, fields, and space-time. Physical nothing in quantum field theory is the vacuum state, which is the lowest energy state of something. It is not the absence of the framework. It is a particular configuration within it. This is why the word nothing keeps slipping, like a label that refuses to stay attached to the thing we want it to name. Each time we try to remove content, the theory reveals a deeper layer that remains. Remove matter, and fields remain. Remove particles, and the vacuum state remains. Remove classical determinism, and quantum uncertainty remains. The ladder of absences continues downward, and we have not reached the bottom, which is both unsettling and strangely illuminating. The vacuum is minimal only relative to a chosen theory, and that is an important qualifier. A different theory could redefine what counts as fundamental, and therefore redefine what counts as empty. Even within one theory, different observers can disagree about what no particles means. The vacuum also raises a subtle point about language and thermodynamics, because energy is not the same as usable work. When we say the vacuum has energy, we are not saying it is a reservoir you can tap without cost. The vacuum is the baseline of the theory, and extracting usable work from it would require a lower energy state to dump entropy into. In equilibrium, the vacuum does not offer a free lunch. The Casimir effect does not contradict this, and the reason is hidden in the full system you must count. The plates move because the configuration changes the field's allowed modes, and energy bookkeeping includes the work done and the changes in the system. If you let the plates fall together, you can extract work once, but you must spend work to reset them. You cannot cycle the setup to extract unlimited energy without paying elsewhere. The vacuum's physicality does not imply perpetual motion, and that boundary matters when popular descriptions drift into fantasy. It is tempting to hear vacuum energy and imagine an infinite battery. Physics instead gives a more disciplined picture, where energy is conserved and the vacuum is a state, not a fuel. The vacuum can shift forces and levels, but it does not hand out free power. Still, the vacuum is strange enough to tempt metaphysical conclusions, and we resist them by staying close to what is defined and what is measured. The vacuum is a state with correlations, fluctuations, and measurable consequences. It is described by quantum fields, which are defined by a Lagrangian or Hamiltonian. Those laws specify what counts as energy, what interactions exist, and what symmetries hold. And here a quiet question surfaces, almost unavoidable when you slow down and let the logic settle. If the vacuum is defined by the laws, then the vacuum cannot explain the laws. If the vacuum is defined on spacetime, then the vacuum cannot explain spacetime. The vacuum is not the bottom layer, even if it is the emptiest layer we can test. That brings us back to the documentary's central question, which has been waiting behind every technical definition. What does physics mean by nothing, and can it answer what could exist before the Big Bang? The quantum vacuum refines the meaning of nothing, but it does not dissolve the origin problem. It relocates it, pushing the mystery into the framework itself. If the vacuum is the best candidate for physical emptiness, then the origin question becomes sharper, because it points at what remains after everything else is removed. Where did the fields come from? Why these fields and not others? Why these coupling constants, these symmetries, this particular quantum structure? And most of all, where did the spacetime background come from that allows a vacuum state to be defined? In ordinary quantum field theory, spacetime is given, and that givenness is a quiet assumption with enormous consequences. Fields live on it, and the vacuum is defined relative to its geometry and time coordinate, which determine what lowest energy means. But Chapter 1 warned that spacetime itself may have a beginning, or at least a boundary of classical description. If spacetime is not fundamental, then the vacuum defined on spacetime cannot be the ultimate before. This is the tension we build toward, and it is not just rhetorical because it shows up where our theories collide. The vacuum looks like nothing only from the perspective of particles, because it contains no particle excitations. From the perspective of fundamental ontology, it is a rich object. It contains the full machinery of quantum fields, and it inherits the assumptions of the theory that defines it. So the vacuum is a clue, not a conclusion, and clues are valuable because they tell you where to look next. It tells us that emptiness in physics is not empty. It tells us that the absence of particles does not mean the absence of influence. It tells us that the universe's baseline state is constrained, active, and measurable. But it also tells us that our best nothing still depends on a framework that we have not explained, and that dependence is the real reveal. If the Big Bang is a boundary of spacetime, then a vacuum defined within spacetime cannot simply sit before it. If we want to approach the idea of before the Big Bang, we may need a theory where spacetime itself can emerge, fluctuate, or be replaced. This is where the narrative pivots again, and the pivot is earned by the physics rather than by wordplay. We began by questioning the word before, and then we questioned the word nothing. Now we see that both words point toward the same deeper target. The stage itself, spacetime, may be part of the cast. The next step is to revisit spacetime with sharper tools, because the vacuum's definition leans on time and geometry. General relativity treats spacetime geometry as dynamical, and it predicts boundaries like singularities under broad conditions. To move past the boundary, we must ask what replaces classical geometry when quantum effects dominate. We must ask whether spacetime can be quantized, whether it can tunnel, whether it can have a beginning without a singular point. So we end this chapter with a careful conclusion, and we keep the words as disciplined as the experiments. The quantum vacuum is not philosophical nothing, but it's the closest thing physics can define and test. It has measurable consequences, from forces between plates to shifts in atomic spectra. It may even connect to cosmic acceleration, though the numbers expose a profound mismatch. And that mismatch is a signpost, not a dead end, because it marks the edge of our current synthesis. It suggests that our understanding of vacuum, gravity, and space-time is incomplete. If we want to speak meaningfully about before the Big Bang, we must confront the possibility that space-time is not the ultimate background. We must descend another rung on the ladder toward a theory where the vacuum and the stage are both emergent. Next, we turn from quantum fields on space-time to the question of space-time itself. We ask what it means for time to begin in general relativity, and what quantum gravity might do to that beginning. We return to the universe at large with a stricter definition of nothing in hand, because the word hides assumptions we rarely notice. The vacuum is not blankness, and it is not a simple absence you can point to. It is a physical state that still assumes fields, laws, and space-time, an arena with rules even when no particles are present. In modern physics, even the quietest vacuum is structured, and that structure is not philosophical. Quantum fields still exist there, and their lowest energy state still has measurable consequences. Casimir plates can feel an attractive force, and atomic energy levels can shift. Small effects, but stubbornly real. Those effects arise because vacuum fluctuations alter boundary conditions and mode densities, changing what zero energy can mean in practice. That is already enough to make nothing slippery, because the vacuum is defined relative to a background. If the vacuum needs a stage on which fields are defined, then the stage itself becomes part of the question. We can remove particles, and we can cool matter, but we cannot casually remove the geometry that tells us what distance and duration even mean. Even the act of defining a field value here presumes that here is a meaningful location in space-time. Now the question tightens, and it becomes less comfortable to phrase. If space-time itself is dynamical, can nothing even be defined without it? If time is part of the system, can before survive as a meaningful word? The discomfort here is not poetic, and it is not an argument from ignorance. Before is a relational term, and it depends on a time coordinate that can be extended. If the object we're discussing is time itself, then the grammar of the question begins to wobble, because the reference frame for earlier may be what fails. General relativity begins with a swap of intuitions that still feels radical a century later. Gravity is not a pulling force across empty distance. Gravity is curvature in space-time, and freefall is motion along that curved geometry. In Einstein's view, what we call a gravitational force is often just an object following the straightest possible path in a warped space-time. This idea is easy to say and hard to fully absorb, because it rewires what straight means. In Newton's picture, space is a passive container and time is a universal metronome. In Einstein's picture, the container has elasticity, and the metronome can tick differently depending on motion and gravity. A clock near a massive body runs slower than a clock far away, and that difference has been measured with satellites and precision clocks. A useful visual is not a rubber sheet, but a set of clocks and rulers that fill space. Imagine a lattice of synchronized clocks and evenly spaced meter sticks, hovering in darkness like a delicate scaffold. In a gravitational field, the clocks do not remain synchronized, and the rulers do not remain Euclidean. The distortions are not added on top of space and time, they are what space and time are doing. The central object is the metric, the rule that assigns distances and time intervals, and it is more than a mathematical convenience. The metric is the ruler and clock of the universe. It tells you what counts as straight, and what counts as simultaneous. In mathematical terms, the metric is a tensor field that gives the space-time interval between nearby events. That interval is not just a distance, and it is not just a time. It is a combined quantity that stays invariant even when different observers disagree about space and time separately. The metric does more than measure, because measurement and causality are intertwined. It defines the light cones that separate what can influence what. It sets the causal structure, what counts as time-like, what counts as space-like, and what counts as null. When the metric changes, the shape of those cones changes too, and the map of possible cause and effect shifts with it. Einstein's equations connect that ruler to what fills the cosmos, and the connection is surprisingly democratic. Energy density, momentum flow, and pressure all shape curvature. Curvature then shapes how matter and light move through space-time. The surprising part is pressure. because it does not feel like mass in everyday intuition. In GR, pressure contributes to the stress-energy tensor, so a hot, high-pressure early universe gravitates more strongly than cold dust. Radiation, with its intense pressure, is therefore not just bright, it is gravitationally potent. The equation is often summarized as matter tells spacetime how to curve, and spacetime tells matter how to move. That slogan is not a metaphor. It is a compact description of how the metric and stress energy are locked together. Change one, and the other responds, as if the universe were a coupled system of geometry and contents rather than a stage and actors. This is why expansion is not debris flying into an external void, and it is why outside is the wrong mental picture. Expansion is the metric changing with cosmic time. The distance between co-moving galaxies grows even when they locally sit still. Picture a dark, three-dimensional grid painted onto space itself, faintly glowing like lines on a transparent crystal. Galaxies are like beads embedded in that grid, not bullets moving through a pre-existing emptiness. As the grid stretches, the beads separate while each bead can remain locally at rest. Locally, physics stays familiar, which is why expansion can be easy to miss. At the scale of a solar system or a galaxy, gravity binds matter tightly enough that the metric slow stretching does not tear structures apart. Expansion is a large-scale behavior, visible when you compare regions separated by millions of light years. In between, there is a hierarchy of forces and timescales, and the cosmic stretching is simply not the dominant effect. To model the universe on the larger scales, cosmology makes a bold simplification, and it is bolder than it first sounds. It assumes homogeneity and isotropy, meaning the universe looks statistically the same everywhere and in every direction. This is not claimed for stars and galaxies, but for averages over huge volumes. It is a statement about the universe when you blur your vision until individual structures dissolve into a smooth cosmic fluid. This simplification has a history, and it was not immediately embraced. In the early 20th century, Einstein initially preferred a static cosmos, while others explored dynamic solutions. Alexander Friedman found expanding and contracting universes, and Georges Lemaitre connected expansion to observed redshifts, ideas that later became the backbone of modern cosmology. When Hubble's observations strengthened the case for recession, the theoretical possibilities abruptly became a description of reality. Homogeneity and isotropy are not philosophical preferences. They are empirical approximations, supported by galaxy surveys and by the extraordinary uniformity of the cosmic microwave background. The universe is clumpy on small scales, yet smooth in the statistical sense that matters for cosmic geometry. The CMB in particular looks like a nearly uniform glow with a faint mottled texture, like a cosmic weather map drawn in temperature instead of clouds. Those assumptions lead to the FLRW family of spacetimes. In FLRW, geometry is encoded in a single function of time, the scale factor AT. As AT grows, all large-scale distances grow with it. The FLRW metric also allows different spatial curvatures. Space can be positively curved like a three-sphere, negatively curved like a saddle, or flat like Euclidean space. The scale factor evolves differently depending on what the universe contains and how much curvature it has. The scale factor is not a substance, and it is not a force pushing galaxies outward. It is a bookkeeping of how the metric evolves. It turns the idea of the universe expands into a precise statement about spacetime geometry. When cosmologists say the universe doubled in size, they mean the scale factor doubled. They do not mean there is a center where expansion began. In FLRW, every co-moving observer sees others receding, because the metric itself is changing everywhere. Redshift becomes the clean observational link, and it is one of the most elegant in science. Light traveling through expanding space has its wavelength stretched. The ratio of observed to emitted wavelength tracks how much AT changed during the journey. A vivid way to see it is to imagine a wave drawn on a stretching rubber band. If the band lengthens while the wave is on it, the crests spread apart. The photon's energy drops with the stretching, and the light shifts toward red. This is why redshift is not only a Doppler story, even though Doppler language can be useful. Motion through space can contribute, but the dominant effect on cosmic scales is geometric. The metric changes while the photon is in flight. In practice, both pictures can be used in limited regimes, and they agree when distances are small. Over cosmological distances, the geometric interpretation is cleaner because it respects the global structure of the FLW spacetime. The redshift becomes a record of the universe's changing scale, written into the spectrum of distant galaxies. With FLRW and Einstein's equations, the universe becomes a dynamical system you can run backward, like rewinding a film that also changes the projector. If AT is smaller in the past, matter and radiation were denser. Temperatures were higher because energy was packed into less volume. The scaling laws are simple and powerful. Matter density scales roughly as AT to the -3. Because particles are diluted by volume, radiation scales as AT to the -4. Because photons are diluted and also redshifted. That extra factor matters, and it reshapes the early story. It means radiation dominated the early universe, shaping the expansion rate and the behavior of perturbations. It also means the early cosmos was not just dense, but intensely hot, with particle species appearing and disappearing as the temperature crossed their mass thresholds. In that furnace, reactions that are impossible today were routine, and the contents of the universe were set by thermal equilibrium and freeze-out. Classical GR then delivers an unsettling prediction. For ordinary matter and radiation, the backward evolution drives AT towards zero in finite proper time. Density and curvature grow without bound as that limit is approached. Proper time is the time measured by a clock moving along with the cosmic fluid. It is not a coordinate trick. In the simplest models, a comoving observer can trace a finite amount of proper time into the past before the equations stop behaving. As a T shrinks, the Hubble parameter grows and the expansion rate becomes extreme. The curvature invariants that measure gravitational intensity can blow up. The equations do not merely predict a hot beginning, they predict a breakdown, an instruction written into the math that the classical description is being pushed too far. This is the classical Big Bang singularity. It is not a bright fireball at a point in space. It is a statement that the FLW description reaches a boundary where the equations stop giving finite answers. The word singularity can mislead. It sounds like an object, like a speck of matter sitting somewhere. In GR, it is better understood as a pathology in the spacetime description, a place where the geometry cannot be extended in a smooth way. Infinities in physics are usually warnings, not trophies, and history has trained us to treat them with suspicion. They often mark a regime where a theory is being used outside its domain. The singularity suggests that classical spacetime is an approximation that fails at extreme density. We have seen this pattern before. Classical electromagnetism breaks down at atomic scales, and classical thermodynamics breaks down when fluctuations dominate. The success of a theory in one regime does not guarantee it can be extrapolated without limit. The key issue is not that we dislike large numbers. The issue is that the theory's own geometric notions break. When curvature diverges, the metric cannot serve as a reliable ruler and clock. If the metric is the device that defines intervals, then a divergence is not just a dramatic prediction, it is the loss of the device itself. At that point, asking for the distance or the time before becomes like asking for the north of the North Pole. At this point, we need to say what the singularity theorems actually claim, because the popular story often overshoots the math. Penrose and Hawking proved results that do not depend on perfect symmetry. They show that under broad conditions, classical spacetime cannot be extended indefinitely into the past. Historically, this was a turning point. Early cosmological models could be dismissed as artifacts of symmetry, as if the singularity were a mathematical mirage. The theorems show that the problem is deeper, because it arises from gravity's focusing effect itself. The theorems rely on a few ingredients, and each is physically motivated. They assume a causal structure that prevents time travel pathologies. They assume gravity focuses geodesics, which is captured by energy conditions that ordinary matter typically satisfies. A geodesic is the closest thing spacetime has to a straight line. For massive objects, it is the path of free fall. For light, it is the null path traced by photons. Focusing is encoded in the Raychaud-Hurry equation, which tracks how bundles of geodesics converge or diverge. Under reasonable energy conditions, gravity tends to make neighbouring geodesics converge. In plain language, gravity acts like a lens for world lines. They also assume that trapped surfaces or global expansion conditions occur. In an expanding universe, light cones tip and geodesics can converge when traced backward. The mathematics then forces a conclusion about incompleteness. A trapped surface is a region where even outward-directed light rays are forced to converge, a hallmark of strong gravity. In cosmology, the relevant condition is often global expansion. If the universe is expanding now, then tracing geodesics backward tends to compress them. The conclusion is geodesic incompleteness. Some time-like or null paths cannot be continued to arbitrary values of their affine parameter. In plain terms, there are world lines that hit an edge of classical space-time in finite time. This is a subtle but crucial point. The theorems do not require that curvature becomes infinite everywhere along the incomplete path. They require that the space-time description cannot be extended in a way that keeps those paths complete. This is a precise statement and also a limited one. The theorems do not say there is a literal point of infinite density in nature. They do not say the universe was created from absolute nothing. They also do not tell us what the edge looks like, and that silence is part of the mystery. They do not specify whether it's a bounce, a quantum foam, an emergent phase, or something more unfamiliar. They only tell us that classical GR, under the stated assumptions, runs out of road. They do not specify what replaces the boundary. They only say that within classical GR, spacetime cannot be smoothly extended past a certain limit, given the assumptions. The beginning is a failure of the classical description, not a detailed origin story. That distinction matters because it changes what we claim to know, and it disciplines the narration. We know the equations, and we know their domain of success. When the equations predict their own failure, they are not giving us a photograph of reality. They are pointing to missing ingredients, degrees of freedom, quantum corrections, or a deeper description of geometry. This matters for our central question. If before means earlier along a time-like path, geodesic incompleteness blocks that extension. The word before becomes a demand that classical spacetime cannot satisfy. We can still write down coordinates that pretend to go earlier, but coordinates are not the same as physics. In GR, the meaningful content is in invariance and in the extendability of geodesics. If the geodesics end, the physical time they represent ends with them. Still, incompleteness is not the same as metaphysical finality. It is an invitation to new physics. It tells us that the early universe is where GR must meet quantum theory. This meeting is not optional. Quantum theory governs matter at high energies, and the early universe was a high-energy environment. If spacetime itself is pushed into regimes where quantum affects matter, then geometry must also become quantum, at least in some effective sense. Quantum field theory, as we saw, needs a spacetime background to define a vacuum. GR makes the background dynamical and, near the beginning, unstable as a classical object. The two frameworks lean on each other and then collide. That collision is conceptual and technical. QFT assumes a fixed causal structure, so it can define particles and their modes. In a rapidly changing metric, even the definition of a particle becomes observer-dependent, and the vacuum can look like a bath of excitations. What one observer calls empty, another can describe as populated, because the splitting between vacuum and particles depends on time and geometry. The early universe is therefore not just hot matter in a static box. It is matter, radiation, and geometry evolving together, each influencing the others. The question of nothing becomes inseparable from the question of what the stage is made of. That collision is not abstract. It shows up as a practical limit on what we can observe. Our view of the early universe is filtered through horizons and through the physics of the primordial plasma. Even if the universe had left perfect records, we would still face the speed of light. Signals take time to travel, and the universe has a finite age. That simple fact turns into a complex map of what can be known from where. One key boundary is the particle horizon. Because light travels at finite speed and the universe has finite age, there is a maximum distance from which signals could have reached us. Beyond that, regions are causally disconnected from our past. Visualize it as a growing sphere centered on us, not in space but in space-time, like a translucent bubble expanding through the cosmic timeline. The farther back you look, the smaller the sphere of causal contact becomes. In the early universe, that sphere can be tiny compared to the whole region, that later becomes our observable cosmos. The particle horizon is not the edge of the universe. It is the edge of what can have influenced us since the beginning of the expansion we can model. There may be vastly more beyond it, but it is hidden by causal structure, not by darkness. Another key boundary is the last scattering surface, and it is as much about matter as it is about light. Before recombination, the universe was an ionized plasma that scattered photons constantly. Photons could not travel freely, so the universe was opaque to electromagnetic observation. In that plasma, electrons and protons moved separately, and photons bounced off free charges through Thomson's scattering. The mean free path of a photon was short, so light could not carry images across large distances. The universe was more like the interior of a star than a transparent night sky, bright, dense, and endlessly diffusive. As expansion continued, the temperature dropped, and electrons could bind to nuclei. Recombination is the moment neutral atoms formed in bulk, reducing scattering dramatically. The cosmos transitioned from fog to clarity, and photons began to stream freely. The cosmic microwave background is the afterglow from that transition. It is not light from the singularity. It is light from the time the universe first became transparent, about 380,000 years after the hot beginning. Today that light has been stretched into microwaves, bathing the sky almost uniformly. If you could see it with your eyes, it would be a faint glow in every direction. In radio maps, it becomes a delicate mottling, tiny temperature variations at the level of tens of microkelvin. Those variations are not noise. They are a fossil pattern, preserved because the plasma's last scattering froze a moment of acoustic motion into the sky. So when we say we see the early universe, we mean we see to that surface. We infer earlier times indirectly through imprints on later observables. Direct images of earlier epochs require messengers other than ordinary light. This is an important discipline in cosmology. We do not guess the early universe from nothing. We infer it from consistent traces, abundances of light elements, patterns of anisotropy, and the way structures grow under gravity. Neutrinos and gravitational waves are candidates for deeper views. A cosmic neutrino background should decouple earlier than photons. Primordial gravitational waves could carry information from even earlier, if they exist at detectable levels. Neutrinos interact weakly, so they stop scattering when the universe is much younger and hotter. In principle, they would provide a snapshot from an earlier epoch than the CMB. In practice, detecting that background is extraordinarily difficult, because neutrinos pass through matter almost without notice. Gravitational waves are different. They are ripples in the metric itself, and once produced they propagate with little absorption. If the early universe generated a stochastic background of gravitational waves, it could be a fossil record of physics at energies we cannot reproduce in laboratories. For now, the CMB is the cleanest wall we can touch. It carries temperature, anisotropies, and polarization patterns that encode early conditions. It also reveals puzzles that classical Big Bang evolution does not naturally explain. The CMB is not just a picture, it is a dataset with structure, and its structure has a precise rhythm. Its angular power spectrum, the way fluctuations vary with scale, acts like a fingerprint. Peaks and troughs encode acoustic oscillations in the primordial plasma, frozen into the sky when photons decoupled. Those peaks reflect a competition between gravity pulling matter inward and radiation pressure pushing outward, a cosmic ringing that stopped mid-note when the universe turned transparent. The first is the horizon problem. The CMB temperature is nearly uniform across the sky. In standard Fellard-Biot expansion without new ingredients, widely separated regions were never in causal contact before last scattering. Imagine two patches of sky on opposite sides, separated by tens of billions of light years today. Trace their histories backward in a standard model, and their past light cones do not overlap before recombination. They could not have exchanged heat or information, yet they look almost identical. Uniformity then looks like a coincidence. If regions could not exchange signals or heat, why do they share almost the same temperature? The puzzle is not that the CMB is perfectly uniform, but that it is uniform enough. The small deviations actually sharpen the mystery. The CMB is not featureless, and those tiny fluctuations are the seeds of galaxies and clusters. So the early universe must be uniform in a very specific way. Smooth overall, but with precisely calibrated ripples. The second is the flatness problem. In GR, spatial curvature evolves in a way that makes flatness unstable over time in many scenarios. A universe that is close to flat today must have been extraordinarily close to flat early on. In the Friedmann equations, curvature behaves like a term that can grow in relative importance unless the expansion history suppresses it. If the early universe deviated even slightly from the critical density, that deviation would typically amplify with time. Yet observation suggests the deviation is tiny. This is a fine-tuning statement. It says the initial conditions must be set with extreme precision to yield the observed near-Euclidean geometry. The puzzle deepens because the CMB suggests the universe is very close to spatially flat. Flatness is not just aesthetic, it affects distances, volumes, and the way light rays converge over cosmic scales. When we fit cosmological models to data, near flatness emerges again and again, as if the universe began balanced on a knife edge. The third is the monopole problem. Many grand unified theories predict heavy relics, including magnetic monopoles, produced in the early universe. Standard hot Big Bang evolution would leave too many of them. These monopoles are not the small north and south magnets we know. They are hypothetical topological defects, stable configurations that can arise when symmetries break as the universe cools. If produced abundantly, they would dominate the mass density and alter cosmic evolution. Yet we do not observe monopoles. Either the theories are wrong, or the early universe evolved in a way that diluted such relics. The absence becomes a constraint on the thermal history. This is how cosmology becomes a laboratory. We cannot build a grand unified accelerator, but the universe once ran at those energies. If relics predicted by a theory are missing, the theory must change, or the cosmic timeline must include a mechanism that removes them. These puzzles are not minor bookkeeping issues. They are signals that the simplest extrapolation of FLRW plus known particle physics is incomplete. They point to missing dynamics in the earliest fraction of a second. They also share a theme. Each puzzle is a question about initial conditions that look too special. Why such uniformity? Why such flatness? And why such a clean absence of unwanted relics? At the same time, the singularity theorems keep the pressure on the concept of a beginning. They suggest that classical spacetime has an edge under broad conditions. The puzzles suggest that even before reaching that edge, the initial state looks oddly special. So the Big Bang begins to look less like an event and more like a limit. It is the place where our classical coordinates lose authority. It is also the place where observed regularities demand an explanation beyond naive initial conditions. There is a quiet shift here. The phrase "the beginning" tempts us to imagine a moment like any other, just earlier. GR suggests something different, a boundary to the applicability of the very framework that defines moments. We can now restate the mystery with sharper terms. Nothing in quantum field theory is a vacuum state on spacetime. GR suggests spacetime itself may be past incomplete, so the vacuum cannot simply be placed earlier than the boundary. If the vacuum is defined by modes of fields, and modes are defined by the geometry, then removing geometry removes the definition. The question becomes recursive. To define the vacuum you need spacetime, but to explain spacetime you may want a deeper theory than a vacuum on spacetime. If we want a deeper answer, we need a framework where spacetime can be replaced, extended, or emergent. That could mean quantum gravity modifies the energy conditions behind the theorems. It could mean the classical notion of geodesics is not fundamental. Energy conditions are assumptions about what kinds of stress energy are allowed. Quantum fields can violate some of them in controlled ways, producing negative energy densities in certain contexts. If those violations are relevant in the early universe, the focusing arguments behind incompleteness can change. It could also mean the universe's early history includes a phase that changes causal structure. A mechanism that makes distant regions once nearby could solve the horizon problem. A mechanism that drives curvature towards zero could solve the flatness problem. Notice the logic, because it is easy to mistake it for storytelling. We are not adding complexity for its own sake. We are responding to specific observational facts and to specific mathematical limits, and we are asking what kind of early dynamics could make them natural. This is where inflation enters as a disciplined hypothesis. It proposes a brief era of accelerated expansion driven by a high-energy field state. It changes the causal story, and it changes what initial conditions even mean. Accelerated expansion means the scale factor grows faster than it would in a matter or radiation-dominated universe. In such a phase, a small causally connected patch can be stretched to enormous size. A region that once equilibrated can later appear as widely separated parts of the sky. Inflation also changes how curvature behaves. Rapid expansion drives the curvature term toward irrelevance, making space look flatter. It can also dilute relics, sweeping away unwanted monopoles by expanding the volume so dramatically that their density becomes negligible. Inflation does not automatically answer what came before everything. It can push the boundary earlier, and it can reshape the meaning of before by altering the structure of time slices. It can also generate the primordial perturbations we later observe. Those perturbations are not arbitrary. Quantum fluctuations in the inflating field and in the metric can be stretched to cosmic scales, becoming the seeds of the CMB anisotropies, and later, of galaxies. In that sense, inflation ties the largest structures in the universe to quantum physics. But inflation is also a sign that the beginning is not a single idea. The Big Bang in everyday speech becomes a layered concept in physics. There is the hot, dense phase we can model well. There is the earlier phase we infer from puzzles. There is the boundary where classical spacetime may fail. This layered view changes the emotional tone of the story. The Bang is not necessarily a single explosive moment. It is a succession of regimes, each described by different effective laws, with transitions that leave traces we can still measure. So we end this chapter with a careful pivot. General relativity predicts a universe with a history, and under broad conditions it predicts past incompleteness. Observation then adds constraints that make the earliest conditions look engineered, unless new dynamics intervenes. The question that remains is not only how did it start, but what does start even mean when time is part of the system? If the metric is the clock, what happens when the clock becomes quantum? If horizons limit communication, what mechanism could have coordinated the early cosmos? Next, we follow those constraints into the inflationary proposal. We ask how accelerated expansion rewrites horizons, flattens geometry and seed structure. We also ask what inflation does to the meaning of before, when time itself is part of the system. Inflation enters as a proposal, not a victory lap, because the early universe looks too coordinated. The hot Big Bang model works beautifully once the universe is already hot, expanding, and filled with particles. Yet Chapter 3 left 3 pressures that feel less like missing details and more like structural strain. The cosmic microwave background is smooth across regions that should not have shared signals. Space is nearly flat in a way that seems unstable under ordinary slowing expansion. Exotic relics predicted by high-energy physics are conspicuously absent, as if the universe erased its own fingerprints. Visually, the problem is almost cinematic. Imagine the CMB as a glowing shell around us, a spherical photograph taken when the universe was only about 380,000 years old. The temperature variations on that shell are tiny, tens of microkelvin on a 2.7 Kelvin background. Yet those variations are organized, correlated, and coherent. If you slide a finger across the sky map, the fluctuations look like a gentle mottling rather than chaotic static. That calmness is not just aesthetic. It is a clue about what could and could not have happened before that light was released. The horizon problem is a causal bookkeeping problem, not a complaint about ignorance. In standard radiation and matter expansion, the particle horizon grows too slowly to connect distant points early on. The particle horizon is the maximum distance over which light signals could have travelled since the beginning. It is computed by integrating how far light can move through an expanding metric, and that integral is stingy in the early universe. Opposite sides of the last scattering surface trace back to disconnected patches, each with its own local history. Yet the CMB temperature matches to 1 part in 100,000, as if the sky had time to equilibrate. A useful image is a patchwork quilt stitched without any chance for the patches to meet. Each region should have cooled at its own pace, with its own density and temperature. In ordinary thermodynamics, uniform temperature implies some mechanism for exchanging energy, even if indirectly. In cosmology, that exchange is limited by the speed of light and by the expansion of space itself. So the puzzle is sharp. Why did the universe begin so uniform without a mechanism to spread information? What set the initial conditions so that the sky looks like one coordinated object rather than a collage? Historically, this discomfort grew as observations improved. When the CMB was discovered in 1965, it immediately suggested a hot early universe, but it also raised the question of why the radiation was so isotropic. By the late 1970s, as cosmologists refined the Friedmann equations and particle physicists pushed grand unification ideas, the horizon issue became harder to ignore. The universe did not merely expand, it expanded in a way that preserved astonishing large-scale order. That order is not impossible, but it looks improbable without a dynamical reason. The flatness problem is a dynamical sensitivity problem, not a preference for Euclid. Curvature acts like a term that competes with energy density in the Friedmann equation. In that equation, the expansion rate h depends on the total energy density and on the curvature parameter k. It is convenient to package this as O, the ratio of actual density to the critical density. If O equals 1, the spatial geometry is flat, and the expansion is delicately balanced. If O differs from 1, curvature eventually tries to dominate as the universe expands under deceleration. Under ordinary radiation and matter-dominated expansion, any small early deviation from critical density typically grows with time. That means today's near flatness implies an extraordinary closeness to Porolos's 1 in the distant past. The required tuning is not a metaphysical complaint, it is a quantitative instability. If you run the equations backward, O must approach 1 with increasing precision, reaching fantastically small deviations at very early times. Inflation was designed to make that tuning unnecessary by changing how the curvature term evolves during a brief, accelerated phase. The relic problem is a particle physics problem that becomes cosmology's burden. Grand unified symmetry breaking can create stable defects like magnetic monopoles, cosmic strings, or domain walls. The details depend on the symmetry group and the topology of the vacuum manifold. Monopoles are especially troublesome because they are heavy, stable, and produced copiously in many high-energy phase transitions. A hot Big Bang without extra expansion leaves too many relics per comoving volume. We do not see them, despite decades of searches and strong constraints from cosmic rays, detectors, and astrophysical limits. Here the visuals almost write themselves. Picture an early universe cooling like a forging metal, passing through phase transitions as symmetries break. In condensed matter, cooling can trap defects in a crystal, leaving dislocations and vortices. In quantum field theory, the same logic applies, except the crystal is the vacuum state of fields. If monopoles formed in abundance, they would still be around, wandering through galaxies, occasionally catalyzing exotic processes. Their absence is not a small discrepancy, it is a loud silence. Inflation offers a simple escape by diluting any initial relic density to near zero. The core idea is accelerated expansion driven by something that behaves like temporary vacuum energy. In general relativity, energy density and pressure both gravitate, and the combination that matters for acceleration is R plus T. If pressure is sufficiently negative, the expansion accelerates rather than slows. This is counterintuitive in everyday language, so it helps to translate it plainly. Negative pressure here means the energy does not thin out the way normal matter does as space expands. If the energy density stays nearly constant while space grows, the scale factor can increase almost exponentially. This is not an explosion into space, it is the metric stretching rapidly. Galaxies are not flying through a pre-existing void like shrapnel. Instead, the distance is defined by the geometry increase, and that change is encoded in the scale factor AT. In an inflationary phase, AT grows by a factor of En, where n is the number of e-folds. Even n around 60 is enough to take a subatomic patch and stretch it beyond the observable universe. The numbers are extreme, but they are extreme in a controlled, mathematically precise way. Inflation is usually modelled with a scalar field, often called the inflaton filling space. Scalar fields are the simplest fields in quantum theory, described by a value at every point rather than a direction. The Higgs field is a familiar example. Although the inflaton is not confirmed to be the Higgs, the inflaton has a potential energy landscape that can dominate its dynamics. When the field rolls slowly, its potential energy outweighs its kinetic energy. That potential energy acts like an effective cosmological constant for a short time. The slow roll condition is more than a slogan. It is a set of inequalities. The potential must be flat enough that the field's acceleration is small and its motion is friction dominated by the Hubble expansion. In equations, the friction term 3HFI can keep the field drifting gently, even on a slope. The result is a period where the Hubble parameter is roughly constant and expansion accelerates. This is why inflation can be both brief and powerful, because exponential growth does not need much time to do enormous work. Accelerated expansion rewrites the horizon story by changing what counts as near in the past. A tiny patch that was once causally connected can be stretched to cosmic size. Regions that look disconnected at recombination can share a common pre-inflation history, when they were close enough for light and particle interactions to equilibrate them. inflation does not let signals outrun light. It changes the geometry so the relevant distances were once small. The CMB's uniformity becomes a memory of earlier causal contact, preserved like a stretched photograph. A clean way to visualize this is with comoving coordinates. Comoving distances factor out the expansion, letting you track which patterns are being stretched rather than carried. During standard decelerating expansion, the comoving Hubble radius, roughly (1), grows with time. During inflation, that comoving Hubble radius shrinks, and that reversal is the key. Modes that were once inside the horizon exit it, not because they move, but because the horizon scale changes. The horizon problem becomes a geometry problem with a new answer. Inflation also drives the universe toward flatness through sheer stretching. Spatial curvature scales differently than vacuum-like energy during expansion. In the Friedmann equation, the curvature term behaves like Ka2, so it dilutes as the scale factor grows. Vacuum-like energy stays nearly constant, so it quickly dominates. During inflation, the vacuum-like component stays nearly constant while curvature becomes negligible. After enough E-folds, any initial curvature is diluted below detectability. Flatness becomes an attractor of the dynamics rather than a fragile initial setting. This attractor behavior is one reason inflation felt compelling to many cosmologists in the early 1980s. The proposal was articulated in different forms by several researchers, including Alan Gough's original Old Inflation, followed by refinements that solved its problems. The mechanism evolved quickly, because the first versions had difficulty ending smoothly. Yet the central intuition survived every revision. If the universe underwent a period of accelerated expansion, then large-scale smoothness and near-flatness stop looking like miraculous initial conditions. They become the expected aftermath of a particular phase. The mechanism has a required ending, because our universe is hot and full of particles. Inflation must stop and convert its energy into ordinary matter and radiation. This is the graceful exit problem, and it is not optional. The inflaton must leave the slow-roll regime and begin oscillating or decaying, and that transition must happen in a way that does not leave the universe empty and cold. The ending is not a footnote. It is the bridge back to the well-tested thermal history. In many models, when slow-roll ends, the inflaton rolls into a steeper region of its potential and begins to oscillate around a minimum. Those oscillations behave like a condensate of inflaton quanta, and they can decay into other particles through couplings. The details can include perturbative decays, but also more explosive processes like parametric resonance, sometimes called preheating. Either way, the energy that once drove accelerated expansion must be redistributed into a bath of relativistic particles. The universe must become radiation-dominated because that is the starting point for nucleosynthesis and the later CMB story. That transfer is reheating, and it is where the familiar hot Big Bang begins. Popular language often calls the whole early story the Big Bang, as if it were a single moment. In inflationary cosmology, the hot, dense phase is a consequence of inflation ending. The Big Bang, as a thermal state, corresponds to reheating and subsequent standard expansion. Inflation is the whisper before the fire, and reheating is the ignition that fills space with light, particles, and entropy. For visuals, imagine a dark, rapidly stretching stage with almost no actors on it. Then, as inflation ends, the stage floods with particles like sparks filling a blacksmith's workshop. Energy that was stored smoothly in the inflaton field gets converted into a seething plasma. Temperatures can soar to enormous values, though the exact reheating temperature depends on the model and its couplings. What matters is the qualitative shift. A cold, vacuum-dominated expansion gives way to a hot, radiation-dominated universe. The familiar Big Bang narrative begins not at the start of inflation, but at the end. Reheating sets initial conditions for nucleosynthesis and for everything we observe later. It determines the temperature at which the universe becomes radiation-dominated, and it influences which particle species are produced abundantly. If reheating is too low, some particles never reach thermal equilibrium. If reheating is high, it can populate heavy states that later decay, potentially affecting light element abundances or the cosmic neutrino background. Reheating can also create asymmetries through out-of-equilibrium processes because thermal equilibrium tends to erase net imbalances. In other words, reheating is where the universe's later chemistry and structure get their starting gun. It also marks the point where the inflaton's special role ends, at least in minimal models. After reheating, the universe follows the well-tested thermal history leading to the CMB. The expansion becomes decelerating again, first under radiation and then under matter. The thermal plasma supports sound waves, and those waves leave imprints that we later read in the CMB's acoustic peaks. So inflation does not replace the hot Big Bang. It prepares it, and then hands the story back to standard physics. Inflation is not only a fix for initial conditions, it is also a generator of structure. Quantum fields cannot be perfectly smooth, even in their lowest energy state. The uncertainty principle ensures that field values and their conjugate momenta fluctuate. During inflation, vacuum fluctuations of the inflaton and the metric are inevitable, and they occur on all scales. Accelerated expansion stretches those fluctuations from microscopic to astronomical scales. Modes that begin deep inside the horizon are pulled outside it, where their evolution changes character. The phrase "stretched to cosmic scales" can sound poetic, but it is also literal. A fluctuation that begins with a wavelength far smaller than a proton can, after enough E-folds, become a pattern spanning millions of light years. The expansion does not amplify the fluctuation by pushing on it like a mechanical wave. Instead, it changes the relationship between physical wavelength and the horizon size. The fluctuation's amplitude becomes imprinted as a classical perturbation in the curvature of space-time and in the density of matter. Something that began as quantum variance becomes the initial condition for galaxies. When a mode crosses the horizon during inflation, its amplitude effectively freezes. The fluctuation stops oscillating because causal microphysics cannot act across the stretched wavelength, and the mode becomes squeezed into a state with a well-defined phase relation. Later, after inflation ends, the horizon grows, and those modes re-enter. Their pattern becomes a map of slight over and under densities, encoded as curvature perturbations. Gravity then amplifies those seeds into galaxies, clusters, and the cosmic web, with dark matter providing much of the scaffolding. This is where the central question about nothing returns in a technical form. The seeds come from quantum fluctuations, often described as fluctuations of the vacuum. But the vacuum here is not philosophical nothingness. It is a state of fields on a background. It has structure in the form of correlations, and it has variance even when its average is zero. Inflation uses the fact that the vacuum is not blank. It turns that minimal quantum texture into a cosmic blueprint, and then it lets gravity do the long work of amplification. If you could watch this process in fast motion, you would see an initially smooth fog develop faint ripples. Those ripples would be almost imperceptible at first, like the slightest grain in a photograph. Over billions of years, the ripples would deepen into filaments and knots. Gas would fall into dark matter wells, cool and ignite stars, and the sky would fill with galaxies. The remarkable part is that the statistical properties of those ripples are still visible in the CMB. The universe carries a fossil record of its earliest quantum noise. Inflation makes sharp, statistical predictions, which is why it became central rather than decorative. The simplest models predict adiabatic perturbations, meaning all components fluctuate together so that the relative number densities remain fixed. They predict that the perturbations are nearly Gaussian, so the map is largely described by its two-point correlation function. They predict a power spectrum that is almost scale invariant, with a slight tilt away from perfect scale invariance. They predict correlations that match a specific phase pattern in the CMB. They also predict that perturbations are coherent, producing acoustic peaks after recombination. The phrase "nearly scale invariant" has a concrete meaning. It means that the variance per logarithmic interval in wave number is almost constant, so no particular scale is strongly favoured. In slow-roll inflation, this arises because the Hubble rate changes only slowly while modes exit the horizon. The slight tilt reflects the slow drift of the inflaton down its potential. That tilt is not an embarrassment. It is a handle because it ties observation to dynamics. The universe is not perfectly scale invariant, and that imperfection carries information. The CMB power spectrum is the main scoreboard for these claims. Acoustic peaks reflect sound waves in the photon-baryon plasma before recombination. When photons and electrons were tightly coupled by Thomson scattering, gravity pulls matter into overdensities, radiation pressure pushes back, and the result is oscillation. Inflationary initial conditions set the phases so peaks line up in the observed way. Without inflation-like coherence, many alternatives struggle to reproduce the peak structure. The data from WMAP and Planck strongly support a nearly scale-invariant adiabatic Gaussian spectrum. A vivid way to see this is to imagine a drumhead. The early plasma is not a drumhead, but it supports oscillations with discrete harmonics, and those harmonics leave peaks at predictable angular scales. The first peak corresponds roughly to the sound horizon at recombination projected onto the sky. Subsequent peaks encode the baryon content, the dark matter density, and the expansion history. Inflation's role is not to create the peaks directly, but to set the initial conditions so that the oscillations begin in sync. That synchronization is the coherence that the data reveal. The spectral index is a compressed summary of the tilt, and it is measured to be slightly less than 1. That slight deviation is consistent with slow-roll inflation, where the potential is not perfectly flat and the Hubble parameter drifts. It also constrains the shape of the inflaton potential and the energy scale of inflation. The amplitude of fluctuations fixes a combination of the potential height and its slope, because larger vacuum energy tends to produce larger perturbations. Inflation is therefore not a free story, it is tied to numbers. Each decimal place in the CMB spectrum is a constraint on the early universe's microphysics. Inflation also predicts tensor perturbations, which are primordial gravitational waves. These are ripples in spacetime itself, generated by quantum fluctuations of the metric during inflation. Unlike density perturbations, tensor modes do not directly clump matter. Instead, they leave a distinctive signature in the polarization of the CMB, especially a curl-like pattern called B-modes. The tensor-to-scalar ratio measures their strength relative to density perturbations. Current observations place strong upper limits on that ratio, and those limits already rule out many simple high-energy models. A detection would be profound, because it would connect cosmology to quantum gravity in a rare, testable way. The amplitude of tensor modes is tied to the energy scale of inflation, so measuring them would effectively weigh the potential energy driving the expansion. It would also indicate that spacetime itself was quantized in the relevant regime, because classical gravity alone does not produce the required spectrum. Yet the absence of detection is also informative. It tells us that if inflation happened, it may have occurred at a lower energy scale or with a potential shape that suppresses tensors. Non-detection is therefore not a failure, it is a narrowing. It pushes viable inflationary potentials toward flatter shapes or lower energy scales. It also motivates models with small field excursions or additional dynamics, because large field ranges often produce larger tensor signals. Inflation remains flexible, but not infinitely so, because the CMB keeps tightening the allowed parameter space. The observational status is strong for the general framework, weaker for specific microphysics. We can see the fingerprints of an inflation-like phase, but we do not yet know the exact hand that left them. This split between framework and mechanism is where the mystery deepens instead of closing. Inflation explains why the universe is smooth, flat, and nearly relic-free. It also explains why the CMB has the pattern it has, and why large-scale structure grew from tiny initial seeds. But it does so by positing a new ingredient, a field and potential chosen to produce the right behavior. The origin question is not erased, it is relocated. We trade one kind of unexplained beginning for another kind of unexplained field configuration. The inflaton is not part of the standard model in any confirmed way. It could be a new fundamental field, a composite degree of freedom, or an effective description of something else. In some constructions, it is related to fields that appear naturally in high-energy theories, but those connections remain speculative. Its potential must be unusually flat to sustain slow roll, because steep potentials end inflation too quickly and produce the wrong spectrum. Its couplings must be tuned to reheat efficiently without ruining the perturbation spectrum. These requirements raise questions about naturalness and fine-tuning, because the model must be both powerful and delicate. Even the language of flat potential hides a technical constraint. Quantum corrections tend to make scalar potentials steeper and less protected by symmetries. So building a stable, slow-roll potential can require careful theoretical engineering. At the same time, the inflaton cannot be completely isolated, because it must couple to other fields to reheat the universe. Too strong a coupling can spoil slow roll or generate unwanted features in the power spectrum. Too weak a coupling can leave reheating inefficient, producing a universe that is too cold or too empty. Inflation therefore sits in a narrow corridor between competing demands. initial conditions remain debated even within inflation, despite its reputation as an attractor. Some models claim inflation begins generically from chaotic initial states, because any region with sufficiently high potential energy will inflate and dominate volume. Others argue that a sufficiently smooth patch is needed to start slow roll at all, and that such a patch may itself be rare. The debate is partly technical, because it depends on how one defines probability in a gravitational system. It is also conceptual, because generic is a slippery word when the system includes expanding spacetime. If inflation needs special initial conditions, it may not solve the deeper why this beginning problem. It may simply trade one tuning for another, shifting the question to the pre-inflation state. Yet even this criticism has an interesting twist. Inflation can make a small, smooth region grow enormous, so the required smoothness might be modest in absolute size. The question becomes whether such a region is plausible in whatever theory describes the earlier stage. In other words, inflation may reduce the burden, but it may not remove it. There are also conceptual critiques about predictability. Inflation can be made to fit many outcomes by adjusting potentials and fields, and by choosing different reheating histories. This flexibility is partly a strength, because it can accommodate data without collapsing at the first anomaly. It is also a weakness, because it can blur what is being tested. The best tests target generic predictions like near-Gaussianity, adiabaticity, and phase coherence, not a particular potential. When the data agree, the framework gains credibility, but the microphysical model remains underdetermined. Non-Gaussianity is a good example of a discriminating test. Simple single-field slow-roll inflation predicts non-Gaussianity that is extremely small, often below current detection thresholds. More complicated models can produce larger non-Gaussian signals, but those are increasingly constrained by Planck and large-scale structure surveys, so the sky does not just say inflation happened. It says more specifically that if inflation happened, it likely resembled a simple, nearly Gaussian mechanism. That is a powerful narrowing, even if it does not identify the inflaton. Alternatives exist and must be named to keep the narrative honest. Some propose bouncing cosmologies where contraction precedes expansion, avoiding a singular beginning. Some propose ekpyrotic scenarios with slow contraction smoothing the universe through a stiff equation of state. Some propose varying speed of light or modified gravity in the early phase, changing causal structure without inflation. Many alternatives struggle with the full suite of CMB constraints, especially peak coherence and non-Gaussianity limits. The debate remains active because the origin question is still open, and because the early universe is a rare arena where foundational ideas can leave measurable traces. In practice, the competition is not just about elegance, but about matching a long list of observational facts simultaneously. Any viable model must explain the near flatness, the smoothness, the spectrum of perturbations, the acoustic peak structure, and the tight bounds on isocurvature modes. It must also connect to a reheating-like process that yields the hot plasma required for nucleosynthesis. Inflation's advantage is that it offers one broad mechanism that naturally addresses several of these constraints at once. Its disadvantage is that it introduces new ingredients that are not otherwise confirmed. Inflation's most unsettling extension is eternal inflation, which can arise in many models. Quantum fluctuations can sometimes push the inflaton uphill locally, even while it rolls downhill on average. In those regions, inflation continues, and space expands faster than it decays. Pockets where inflation ends become bubble universes with their own reheating. Each bubble experiences a local hot Big Bang with its own initial conditions and potentially its own low-energy physics. The visuals here shift from a single expanding fireball to a branching cosmic landscape. Imagine a vast inflating background, dark and rapidly swelling, in which bright bubbles nucleate like droplets forming in a supercooled vapor. Each bubble is a region where inflation has ended, where energy is converted into particles, and where a hot universe begins. The bubbles grow, but the background grows faster, so inflation never ends everywhere at once. The global structure can be fractal-like, with inflation continuing indefinitely into the future in some regions. This is a radical shift in what before the Big Bang could mean. In that picture, the Big Bang is no longer the beginning of everything. It becomes a transition event inside a much larger inflating spacetime. Our observable universe is one reheated region among many, and the boundary of our view is not the boundary of reality. The phrase multiverse enters cautiously here because it carries philosophical baggage, yet the underlying idea is technical. If the dynamics of inflation generically produce many reheating events, then many causally disconnected regions may exist. The unsettling part is not the multiplicity itself, but what it does to explanation. Eternal inflation also introduces the measure problem, which is a technical form of ambiguity about probabilities. If infinitely many bubbles form, counting outcomes becomes ill-defined, because every allowed event happens infinitely many times. Different ways of regulating infinities can give different predictions, and the choice of measure can look suspiciously like a choice of answer. This is not a minor detail, because it affects whether the framework is predictive. It also intersects with anthropic reasoning, which can sound like explanation but often functions as selection. If we only observe regions compatible with observers, how much of the theory is being tested? This is where the narration has to be careful. The measure problem is not a rhetorical trick, and it is not a mere philosophical quibble. It is a mathematical problem about defining probabilities in an eternally reproducing space-time. Cosmologists have proposed various measures, each with strengths and pathologies, and no consensus has fully settled the issue. The presence of this problem does not falsify inflation, but it complicates its most expansive versions. It suggests that some extensions may outrun our current ability to extract clear predictions. We should separate what is well supported from what is speculative. The evidence supports an early period that produced near-scale invariant coherent Gaussian perturbations. The evidence supports a universe that is very flat and very smooth on large scales, and it supports a thermal history consistent with reheating and standard expansion. Inflation is the leading framework that unifies these facts with one mechanism. Eternal inflation and a multiverse are plausible in some models, but they are not established by current data. The sky has told us a lot, but it has not told us everything. Even without a multiverse, inflation pushes the origin question backward. If inflation happened, what set the inflaton in its special state? Why did the potential have the right shape and energy scale to produce roughly 60 e-folds, the observed amplitude and the observed tilt? Why did inflation start at all, and why did it end when it did, rather than continuing too long or stopping too soon? The whisper explains the fire's uniformity, but not the match that lit the whisper. And once you notice that, the mystery becomes sharper rather than softer. This returns us to the documentary's central question with sharper edges. Physics can replace naive nothing, with a quantum vacuum and with fields in special states. It can replace before with causal structure and geodesic extendability. Inflation shows how a particular state can reshape horizons and seed structure, turning quantum variance into classical patterns. But it does not yet tell us why there is a state, a field, or a space-time to inflate. It gives us a mechanism, and then it points beyond itself. There is also a deeper tension with beginnings that inflation cannot fully dissolve. The Hawking, Penrose singularity theorems can be evaded if certain energy conditions are violated, and inflation uses stress energy with negative pressure. Quantum fields can violate classical conditions in subtle ways, so the door is not locked. Yet many results, like the Borde-Guth-Vilenkin theorem, suggest inflationary spacetimes are still past incomplete under broad assumptions. Even an eternally inflating future may have a boundary in the past, a limit to how far the inflationary description can be extended. Past incomplete does not necessarily mean a singularity like the classical Big Bang singularity. It means that the spacetime cannot be extended indefinitely along past-directed geodesics within the inflationary framework. There is, in that sense, still a before that inflation does not describe. The implication is not that inflation is wrong, but that it may be a bridge rather than a foundation. It may be a phase in a larger story, and the earlier chapters of that story may require a deeper theory of spacetime itself. So inflation may be a bridge, not a foundation. It connects quantum fluctuations to cosmic structure with remarkable economy, and it does so with equations that tie directly to data. It explains why the universe looks older than its causal horizon would suggest, because the horizon itself was reshaped. It makes flatness and relic absence natural outcomes of dynamics, rather than miracles of initial tuning. But it also points to a deeper framework where space-time and fields are not simply given. The more inflation succeeds, the more it highlights what it assumes. Now, the narrative turns from an early expansion phase to the question of what space-time is made of. If inflation needs a background and a field, we ask where those come from, and whether background is even the right word at the deepest level. If inflation is past incomplete, we ask what replaces the boundary, and whether time itself emerges from something more fundamental. The next chapter moves toward quantum gravity, where geometry itself can emerge or tunnel. We keep the mystery alive because the universe keeps leaving clues, and because every solved problem seems to expose a deeper one. We move from inflation's successful predictions to its unanswered premises, and that shift changes the emotional temperature of the story. We trade a single beginning for a layered sequence of transitions, each with its own physics and its own unanswered questions. The Big Bang becomes a local thermal start, not necessarily the start of time. Nothing becomes a ladder again, with inflation occupying one rung above deeper absence. The next step is to ask whether space-time can be born from a quantum description at all, and whether the whisper itself came from silence, or from something stranger. Inflation gave us a powerful bridge, but it still assumes a stage, and that assumption is exactly where the puzzle tightens. The central question returns with sharper teeth, because the stage itself may be optional in the deepest description. What does physics mean by nothing, if space-time is not guaranteed to exist as a background? General relativity treats geometry as smooth and classical, like a continuously curved fabric that can be stretched without tearing. Quantum theory treats matter and fields as probabilistic, and it often reveals discreteness in outcomes, even when the underlying equations look continuous. Near the Big Bang, both claims are pushed to their limits, and neither can be safely ignored without losing contact with reality. The reason is scale, not philosophy, because nature changes character when we probe far enough down into its structure. There is a regime where length, time, and energy reach Planck units, and our familiar approximations lose their footing. Around 10⁻⁵ meters and 10⁻⁴ seconds, quantum fluctuations of geometry should matter, not as a tiny correction but as the main event. Those numbers are not arbitrary, and their origin already hints at the conflict we are trying to resolve. The Planck length combines Newton's constant, the speed of light, and Planck's constant into a single scale, as though gravity, relativity, and quantum mechanics are forced into the same sentence. The Planck time is that length divided by light speed, a minimum tick suggested by dimensional analysis rather than by any built-in cosmic clock. The corresponding Planck energy is enormous by particle standards, implying that to probe that small, we must concentrate energy so intensely that gravity cannot stay quiet. To picture that scale, imagine a ladder of zooms that never stops, and imagine the camera refusing to settle. Galaxies shrink into clusters, then into stars, then into atoms, and then into a blur where distance becomes a question rather than a measurement. At the Planck length, the energy required to localize anything would curve spacetime so strongly that the measurement disturbs the very ruler. The act of asking where becomes inseparable from the gravitational response, because the probe and the geometry cannot be cleanly separated. At those scales, classical spacetime is not a reliable background, because the background becomes part of the quantum system. Curvature becomes extreme, and the metric stops behaving like a stable ruler that every observer can share. The singularity is less a point in space, and more a warning label that says the classical description has been overextended. It marks the boundary of a map, not necessarily the boundary of the territory. In Chapter 3, geodesics ran into an edge, as though the lines of freefall simply stopped in mid-sentence. In Chapter 4, inflation likely remained past incomplete under broad assumptions, even when it smoothed and stretched the cosmos into near uniformity. Both pressures point to the same missing piece, a quantum theory of gravity that can speak before the classical script begins. The question is not whether our equations are elegant, but whether they are still allowed to talk at those densities. Quantum gravity is required because gravity couples to everything, including vacuum energy and quantum fluctuations that never fully disappear. If energy and momentum are quantized, then the geometry responding to them cannot remain purely classical without contradiction. The early universe is where that mismatch becomes unavoidable, because densities and curvatures approach the regime where quantum back reaction is not optional. Even the notion of empty becomes charged, because the vacuum is not truly still. There is also a practical tension built into our best theories, and it shows up whenever we try to take them seriously together. Quantum fields, even in their lowest energy states, contain zero-point fluctuations that contribute to stress energy. General relativity, meanwhile, insists that stress energy shapes curvature and curvature shapes motion in return. When the fluctuations are large and the curvature is large, the feedback loop becomes violent, and the classical approximation can break. In ordinary settings, we hide this violence behind effective descriptions that work astonishingly well. Renormalization lets quantum field theory make precise predictions, even though naive calculations can diverge. In curved space-time, those same vacuum effects can become physical, as in Hawking radiation or the Unruh effect, where particles depend on the observer's motion. Near the Big Bang, that observer dependence is not a subtlety, because there may be no stable notion of an observer at all. This forces a conceptual shift, and it is one of the chapter's quiet revolutions. Quiet only because it arrives through mathematics rather than spectacle. Space-time may be emergent, like temperature emerging from molecules, even though temperature feels fundamental in daily life. Geometry may be a quantum variable, not a fixed arena, and it may have superpositions rather than a single definite shape. What we call space and time may be approximations that appear only in certain states, the way a smooth ocean surface appears from countless moving atoms. If that sounds abstract, the visual intuition can be made almost tactile. Imagine a grid drawn on a rubber sheet, then imagine the grid itself starting to shimmer and jitter, as though each line is uncertain where it belongs. Now imagine that the sheet is not sitting in a room, because the room is also part of the sheet. The stage lights dim, and the only thing left is the pattern of relations that can stabilize into something stage-like. The shift is not only about small distances, because it also reaches into the meaning of time itself. In quantum mechanics, time is usually an external parameter, a background label that tells a wave function when to evolve. It is not typically an operator like position or momentum, and it is not usually something that can fluctuate. That asymmetry is harmless in a laboratory, where space-time is assumed to be there, and where clocks can be treated as classical devices. In general relativity, time is part of the dynamical system, woven into the metric that can stretch and tilt. The theory is invariant under different choices of time coordinate, because no single slicing of space-time is privileged. When you quantize gravity, that symmetry becomes a problem of definition, because the usual notion of evolution in time depends on a clock you no longer have. The equations do not tell you which variable deserves to be called time, because the theory refuses to privilege one. This is the problem of time, and it is more than a technical nuisance that can be postponed. In canonical quantum gravity, the fundamental equation often looks timeless, as though the universe's state is constrained rather than evolving. The universe's quantum state does not obviously change with an external clock, because there is no external clock to appeal to. The familiar story of causes preceding effects begins to wobble, not because causality is denied, but because the ordering parameter is no longer guaranteed. Historically, this tension emerged as physicists tried to combine the Hamiltonian form of general relativity with quantum principles. The Wheeler-DeWitt equation became a symbol of the issue, because it resembles a Schrödinger equation with the time derivative missing. That absence is not a typo, and it is not merely aesthetic. It is the mathematical reflection of a universe that contains its own clocks, rather than being watched from outside. So the question, what happened before the Big Bang, may be ill-posed in the deepest description, even if it feels unavoidable in human language. Before assumes an ordering parameter that may not exist fundamentally, at least not in the same way it does in classical spacetime. Time might emerge only after a transition into a semi-classical geometry, when a particular state makes a clock-like variable behave reliably. The question may need translation, not just a new answer. What would such a translation look like in plain terms? Instead of asking for an earlier moment, we might ask for a more fundamental description from which moments can be derived. Instead of a timeline, we might have a network of correlations, where earlier and later appear only when the correlations become stable enough to mimic a clock. The unsettling possibility is that the universe can have structure without having time in the way we instinctively imagine it. Quantum cosmology is the attempt to apply quantum principles to the universe as a whole without stepping outside it. Instead of quantizing particles on spacetime, it quantizes spacetime itself along with matter and radiation. The goal is a wave function of the universe, a compact object meant to encode what can be said about all possible cosmic configurations. It is a bold move, because it asks quantum theory to operate without its usual separation between observer and observed. A wave function of the universe is not a wave in space, because space is part of what it describes. It is a function on a space of possible geometries and field configurations, often called configuration space, or, in simplified models, mini-superspace. It assigns amplitudes to entire cosmic histories, not to events inside one history, and that shift changes what counts as a state. The mathematics becomes less like tracking a particle, and more like weighting possible worlds. In mini-superspace, we deliberately compress the universe's complexity, keeping only a few degrees of freedom such as the scale factor and one or two fields. That simplification is not a claim that the universe is simple, but a way to make the conceptual issues calculable. It is like studying ocean waves by first learning the behavior of a single ripple in a controlled tank. The danger is that we may miss crucial turbulence, yet the benefit is that we can see the skeleton of the problem. This changes what probability means, and it changes it in a way that is easy to underestimate. In ordinary quantum mechanics, probabilities refer to measurement outcomes in time, with an external observer and an external clock. In quantum cosmology, the system includes the clock and the observer, so interpretation becomes delicate and sometimes controversial. We are forced to ask what it means to condition on an observation when the observer is part of the wave function. One response is to focus on conditional probabilities, where one variable plays the role of a clock relative to which others change. Another is to emphasize decoherence, where interactions among degrees of freedom suppress interference between different branches. In that view, classical spacetime is not assumed, but selected as a stable pattern that resists quantum mixing. The universe looks classical not because it must, but because certain states become robust under their own internal entanglement. One tool is the path integral approach, which borrows its logic from quantum field theory and extends it into geometry. Instead of a single trajectory, you sum over possible geometries weighted by an action, and you allow matter fields to fluctuate along with them. Each history contributes a complex phase, and interference decides which coarse-grained behaviors dominate. In a semi-classical limit, the dominant contributions resemble classical spacetimes, as though classical geometry is the most stable pattern in the quantum sum. Visually, the path integral is a kind of cosmic multiple exposure. Countless faint outlines of possible universes overlap, and most cancel one another through destructive interference. A few patterns reinforce, becoming bright enough to look like a single coherent history. The classical universe we inhabit may be the sharp ridge of that interference landscape, the path that survives the quantum blur. This is where proposals about the beginning can be stated precisely, even if they remain speculative. They are boundary conditions on the universe's wave function, which means they specify how the path integral is to be taken. They are not yet established facts, but they are mathematically definable possibilities that can be compared for consistency and, in principle, for observational consequences. The beginning becomes a choice about what histories are allowed and what kinds of geometry are permitted to contribute. One influential idea is the Hartle, Hawking no-boundary proposal. Developed in the early 1980s as quantum cosmology matured, it suggests the universe has no initial boundary in the classical sense, no sharp starting surface where equations must be patched by hand. The earliest regime is described by a smooth Euclidean-like geometry, where the metric signature resembles space rather than time. In that regime, the path integral is dominated by compact geometries that close off without an edge. The historical context matters because it shaped what natural meant to the people proposing it. Hawking's work on black holes had already made horizons, and Euclidean methods feel physically consequential rather than merely formal. Hartle and Hawking then asked whether the universe itself could be treated with similar tools, using regularity as a guiding principle. In a field full of infinities, a condition that removes a singular boundary has a certain gravitational elegance. Visually, this picture invites a slow camera move across a surface that has no seam, and the motion is deliberately unhurried. The grid lines of space-time, which later look like time flowing upward, begin by curving gently into a rounded shape. There is no jagged cliff labelled T Jazero, only a region where the meaning of time direction is not yet defined. The universe begins, in this view, the way a sphere begins, smoothly, without corners. In that picture, time behaves like a spatial direction near the origin, and the distinction between temporal and spatial directions becomes blurred. The geometry closes off smoothly, avoiding a singular edge where curvature would blow up. The beginning is replaced by a rounded cap in the mathematical description, a place where the classical notion of a time coordinate fails gracefully. It is a proposal about regularity, not a poetic metaphor, and it lives or dies by the consistency of the quantum weighting. The analogy is the South Pole, and it is used because it is concrete enough to picture while still being faithful. There is no point south of it, yet the surface is well defined, and the geometry does not break. The beginning is not an edge where physics stops, but a place where the notion of time changes character. If you insist on asking what lies before, you're like a traveller asking what lies south of south, and the question misfires because the coordinate system has changed. Time then emerges as the geometry becomes Lorentzian and classical, and the difference between time-like and space-like directions becomes meaningful again. The transition is not a moment inside time, but a change in the kind of metric that defines time in the first place. The proposal aims to dissolve the need for a prior time, while still producing a universe that later behaves like the one we observe. It trades a singular boundary for a smooth quantum condition, and it asks us to accept that the earliest region is not temporal in the usual sense. A different boundary condition is Vilenkin's tunneling proposal, which uses a different quantum intuition and a sharper sense of emergence. It treats the universe as nucleating through a quantum process, analogous to tunneling in ordinary quantum mechanics. The universe tunnels into a classical expanding state from a regime without classical spacetime, and the wave function is chosen to represent an outgoing expanding branch. The emphasis is on appearance as a quantum event, rather than closure as a geometric cap. The phrase tunneling from nothing is easily misunderstood, and the misunderstanding matters because it invites the wrong kind of argument. It does not mean philosophical nothingness, with no laws, no structure, and no mathematical framework. It means the absence of a classical spacetime manifold within the model's configuration space, so there is no prior classical geometry to stand on. The word nothing is a technical label, not a metaphysical victory, and the theory still assumes a rulebook for amplitudes. In tunneling language, the nothing is a boundary of superspace, where the scale factor goes to zero and the classical notion of size disappears. The proposal assigns a specific outgoing wave condition, which is meant to select expanding universes rather than contracting ones. In simplified mini-superspace models, this choice changes which semi-classical histories are weighted more heavily. The universe is treated as a quantum system that can appear in an allowed region of configuration space, like a particle appearing on the far side of a barrier. If you visualize it, the scene is not an explosion in an empty void. It is a landscape of possible geometries, with a forbidden region where classical evolution cannot proceed, and a faint quantum seepage across that boundary. On the far side, a classical expanding branch sharpens into view, as though the wave function has found a corridor where spacetime can behave like spacetime. The drama is not in a pre-existing arena, but in the emergence of the arena itself. Both no boundary and tunneling are attempts to replace a singular start with a quantum condition, and both are shaped by what they consider physically natural. They differ in mathematical choices and in what they predict for inflation's likelihood, because the wave function's weighting can favour different initial field values. They also share a limitation, because interpretation and measure remain contested, and because simplified models may hide crucial degrees of freedom. The proposals are crisp on paper, yet slippery when translated into observational bets. These are not the only approaches, and the landscape of quantum gravity is famously plural, almost uncomfortably so. Quantum gravity is a frontier with multiple competing frameworks, and it is not yet clear which language is closest to nature. The shared intuition is that spacetime may not be fundamental, even if it is our best macroscopic description. The disagreements are often about what replaces it, and what counts as a prediction that cannot be tuned. String theory offers one route, and it began as an attempt to tame quantum field theory's divergences by replacing point particles with extended objects. It naturally includes a massless spin-2 excitation identified with the graviton, which is why it is taken seriously as a quantum gravity candidate. It also suggests extra dimensions, typically compactified, and it reveals dualities where geometry can be traded for other variables. In some cases, a large space can be equivalent to a small one, and a curved space can be equivalent to a different theory without gravity. From a visual standpoint, string theory invites a strange kind of elegance that feels almost musical. A point becomes a vibrating filament, and different particles become different modes of the same underlying object. Extra dimensions are not added as scenery, but as hidden directions that influence the spectrum of vibrations. Geometry becomes less like a fixed stage, and more like a parameter in a deeper quantum system, one that can be reshuffled without changing the physics. In holographic ideas, space-time volume can be encoded on lower dimensional boundaries, and the claim is not merely philosophical. The degrees of freedom scale like area, not volume, as black hole entropy already hints through the Bekenstein-Hawking formula. That scaling suggests that the interior geometry is an emergent bookkeeping of deeper quantum information, rather than a fundamental container. If true, then inside is not primary, and the universe's bulk may be a kind of projection, solid to us, yet derivative in the accounting. Another route is loop quantum gravity, which quantizes geometry directly rather than embedding it in a larger framework. Areas and volumes become discrete spectra, like quantized energy levels, and the continuum metric emerges only as an approximation to many quantum excitations. The basic variables are chosen to respect general relativity's gauge structure, and the resulting quantum states resemble networks of links and nodes. The smooth geometry we experience would then be a coarse-grained limit, like a fluid emerging from molecules, even though no single molecule is wet. Loop quantum cosmology applies that quantization to highly symmetric universes, where the complexity is reduced but the key effects can be studied. It modifies the Friedmann equations at extreme density, introducing corrections that are negligible at low curvature but dominant near the Planck regime. The key claim is that quantum geometry produces an effective repulsion near Planck density, not by adding exotic matter, but by changing the gravitational response. The equations that once drove collapse can reverse sign when discreteness becomes important, as though gravity changes its mind at the smallest scales. In LQC, the Big Bang singularity is replaced by a bounce, and the imagery is almost cinematic in its clarity. A contracting universe shrinks as densities rise, then reaches a minimum scale factor, and then re-expands into a new classical branch. The before becomes a prior branch of cosmic history, at least in the effective description used to connect quantum dynamics to classical observables. The singular wall becomes a turning point, and the timeline becomes a curve that dips and rises. The mechanism is not a new force added by hand, and that is part of its appeal to many researchers. It arises from the discrete structure of geometry in the quantized theory, which alters how curvature responds to energy density. When density approaches a critical value, the effective dynamics reverse the collapse, and the Hubble parameter passes through zero. The bounce is a dynamical consequence of the quantization scheme, not a narrative patch, and it can be derived in controlled symmetry-reduced settings. A bounce changes the narrative stakes, because it turns the beginning into a transition rather than an absolute origin. It also raises new questions about initial conditions, entropy, and whether contraction can remain smooth enough to avoid chaotic anisotropies. If there was a long contracting phase, what sets its arrow of time, and what prevents it from becoming highly inhomogeneous? The bounce solves one problem while sharpening others, and it forces us to confront how fragile smoothness can be under gravitational collapse. LQC also invites observational tests, which is where the mystery meets discipline, and where speculation must learn restraint. A bounce can modify the primordial power spectrum through pre-bounce evolution and matching conditions, especially for the largest observable scales. It can produce features like running, oscillations, or suppressed power on large scales, depending on how modes evolve across the bounce. In some treatments, it can also affect the phase of perturbations, leaving subtle correlations that might show up as anomalies rather than as clean peaks. The challenge is degeneracy, and it is a recurring theme in early universe science that refuses to go away. Many inflationary potentials and many pre-inflation histories can mimic similar spectra, especially once reheating and late-time effects are included. Extracting a unique bounce signature requires precision and a clear prediction that cannot be tuned away by adjusting other parameters. Otherwise, a bounce becomes a story that fits after the fact, and cosmology cannot afford too many stories. Another family of alternatives is ekpyrotic and cyclic cosmology, which reuses some of the same goals but changes the route. Instead of early accelerated expansion, it uses a slow contraction with a stiff equation of state, meaning pressure is large compared to energy density. That contraction can smooth and flatten the universe by suppressing anisotropies and curvature, because the stiff component can dominate the energy budget. The smoothing happens not by stretching space, but by dynamically damping unwanted deviations, like friction that becomes stronger as the universe tightens. In some versions, the scenario is motivated by brains in higher dimensions, echoing ideas already hinted at in string-inspired settings. A collision or close approach triggers a hot big bang-like phase, converting kinetic energy into matter and radiation. The bang becomes a brain interaction rather than a singular creation event, and the classical singularity is replaced by a higher dimensional process. The four-dimensional description is then an effective shadow of a deeper geometry, one that we infer rather than directly observe. Ekpyrotic contraction addresses horizon and flatness differently than inflation, but it aims at the same observational targets and must hit the same numerical marks. A long, slow contraction can bring regions into causal contact before the hot phase, which can help with the horizon problem. It can also dilute curvature relative to the dominant stiff component, driving the universe toward flatness in a different dynamical way. The smoothing is subtle, and it depends on maintaining the right conditions through contraction, because contraction is a dangerous time for instabilities, but it faces its own hurdles, and the hurdles are not minor technicalities that can be waved away. Generating the observed nearly scale invariant, Gaussian, adiabatic perturbations is non-trivial, because simple ekpyrotic models tend to produce a different spectrum. Many models require multiple fields or special conversion mechanisms to match CMB constraints, and those mechanisms introduce their own parameters. The theory must also navigate the transition through the bounce or collision without spoiling the perturbations, because a beautiful spectrum can be ruined by a messy handoff. Cyclic models add an even stronger claim, and they do so with a kind of audacity that is hard to ignore. The universe undergoes repeated phases of contraction and expansion, and each cycle is meant to set up the next. Each cycle resets conditions, at least partially, and the Big Bang is one transition in a long sequence rather than the first page. The appeal is that initial conditions may be replaced by attractor behavior, though the details are demanding, and the bookkeeping of entropy becomes a central concern. The test is again in the sky, because cosmology ultimately answers to data, not to narrative satisfaction. Cyclic and ekpyrotic models can predict distinctive non-Gaussianity shapes, a blue tensor spectrum, or specific features in the scalar spectrum. They can also predict relics from prior cycles, though those claims are model-dependent and often fragile. The observational signatures are not guaranteed, but they provide a way to keep the ideas accountable, and accountability is what separates physics from mythology. Across all these approaches, one theme keeps returning, and it is the chapter's anchor even as the details diverge. The Big Bang singularity is likely not a physical event inside classical spacetime, like an explosion at a location. It is a sign that classical spacetime is an emergent approximation that fails in an earlier regime. The singularity is the theory telling us where it stops being trustworthy, and it is doing so in the only language it has. That does not automatically mean nothing existed, and it does not automatically mean something existed in the everyday sense. It means the question must be rephrased in the language of the deeper theory, whatever that theory turns out to be. The options include a timeless quantum regime, a bounce from contraction, or nucleation into a classical phase. Each option changes what counts as a prior state, and each option changes what nothing could mean. This is where we separate mathematical possibility from established fact, and the separation matters for honesty. Quantum gravity models can be internally consistent and still be wrong about nature, because consistency is not the same as confirmation. The early universe gives us limited data, and many models can be fit to the same observations with different microphysical stories. The silence of direct Planck-scale experiments forces us to be careful, and it forces us to treat elegance as a clue rather than a verdict. Historically, this caution was learned the hard way, and cosmology carries that memory in its methods. General relativity itself was once a bold extrapolation, later anchored by observations like light bending and gravitational redshift. Inflation began as a theoretical fix for puzzles, then gained support through its perturbation predictions, though its microphysics remains open. Quantum gravity now sits at a similar threshold, rich in ideas but hungry for decisive evidence, and the community knows how long that hunger can last. Testability is the discipline that keeps mystery grounded, and it is the reason we keep returning to the sky with better instruments. The CMB and large-scale structure constrain the scalar tilt, its running, and departures from Gaussianity, all of which encode early universe dynamics. Polarization constrains tensor modes, and the energy scale of inflation-like phases because primordial gravitational waves would imprint a specific B-mode pattern. Each constraint is a boundary on what the beginning could have been, and the boundaries are tightening year by year. Future probes widen the net, and they do so by adding both precision and new windows that were once unimaginable. Improved B-mode searches can tighten tensor limits, or detect a primordial background, which would immediately reshape the space of viable models. Large-scale structure surveys can constrain non-Gaussianity and features across many scales, using galaxies as traces of primordial statistics. Even small shifts in error bars can rule out entire families of early universe mechanisms, and that is why patience becomes a scientific virtue. Other messengers matter too, because the early universe could have left signals outside the CMB, in frequency bands and channels we are only beginning to access. A stochastic gravitational wave background at different frequencies could reveal phase transitions or pre-Big Bang dynamics, depending on when and how it was generated. Relics like cosmic strings would leave lensing signatures and gravitational wave bursts, acting like fossilized defects from high-energy physics. Each messenger is a different kind of memory, and each memory has its own distortions, yet underdetermination remains a central obstacle, and it is not merely a philosophical complaint dressed in formal language. Different microphysical stories can produce similar effective spectra after reheating, because late-time evolution can wash out details. Even if a signal is detected, mapping it uniquely to a quantum gravity mechanism may be difficult, especially if multiple parameters can be adjusted. The universe can be generous with patterns and still be stingy with explanations, and that stinginess shapes the frontier. So the honest stance is layered, and it resists simple slogans that promise closure. We have strong evidence for a hot early universe, and for inflation-like perturbations that seeded structure. We have strong reasons to expect classical GR fails at the Planck regime, because quantum fluctuations of geometry cannot be ignored there. We do not yet have a confirmed quantum gravity theory, and we do not yet know which proposal, if any, is the right replacement. Still, the frontier has sharpened what before could mean, and that sharpening is progress even when it feels unsatisfying. If time emerges, before may be a category error, a word that presumes what the theory denies. If a bounce occurs, before becomes a real earlier branch, but not necessarily an earlier time in the same metric, because the effective time parameter may change character. And if the universe nucleates, before may refer to a regime without classical spacetime described only by a quantum state. In each case, nothing is not empty space, because empty space is already a structured stage with geometry and fields. It is either a quantum configuration space, a boundary condition, or a deeper substrate whose variables do not resemble space and time. The word nothing becomes a placeholder for not the classical manifold we are used to. That is a smaller claim than it sounds, and it is also a stranger one because it asks us to accept that our most basic intuitions may be emergent conveniences. This chapter's conclusion is not a solution, but a narrowing of the question, and narrowing is sometimes the most honest kind of advance. The Big Bang may be a beginning of time, a transition from quantum geometry, or a local event in a larger cosmos. Each option changes what nothing can mean, and each option changes what counts as an explanation. The mystery remains, but its contours become sharper, and the sharpness is a kind of knowledge. Now we pivot from models to meaning. After exploring physical mechanisms, we confront the deepest layer, where language itself begins to strain. Can nothing ever be literal in physics? And how does explanation work when time itself begins? If causality is normally a relation across time, what becomes of it when time is emergent? We carry one final clue forward, and it is easy to overlook because it is so familiar. The universe leaves imprints, even from its earliest accessible moments, and those imprints survive as patterns in the sky. The mystery is not only that we lack answers, but that we have data at all, as though the beginning left fingerprints on the cosmos. The question becomes not just what happened, but why anything is knowable, and why the universe is legible to creatures who arrived so late. Next, we step from quantum gravity's proposals to the philosophical edge they force. We ask what causality means without time, and what counts as an explanation when the clock is part of the system. The physics has brought us to a threshold, and the next step is to ask what it means to cross it. We have chased the Big Bang down to the edge of spacetime's reliability. Now the question changes shape, because explanation itself starts to wobble. In the visuals, the familiar cosmic timeline begins to fray at the left edge. Dates and temperatures fade into mist, and the neat axis of time looks less like a ruler. The closer we push toward the beginning, the more our language starts to sound like it is walking on ice. We keep saying nothing as if it names one thing. In physics, it names a ladder of absences, and each rung carries hidden structure. A ladder is a useful image because it suggests order, but it also suggests danger. Climb down far enough, and the rungs themselves may be made of assumptions. At the bottom, even the idea of down becomes questionable. First is empty space, the everyday void with geometry still intact. It has distances, durations, and a place for fields to live. Empty space is not merely where nothing happens. It is a stage with a metric, a way to measure intervals, and a causal structure that tells light how to travel. Even if you remove every atom, you still keep the coordinate grid, at least as an idealization. In classical physics, this rung feels intuitive. You can imagine a box pumped to near-perfect vacuum, with the walls cold and silent. Yet the box still has volume, the clock still ticks, and the electromagnetic field still has a definition. Second is the quantum vacuum, the lowest energy state of fields on spacetime. It is not featureless, because fluctuations and correlations remain. Here, vacuum means a state, not an absence. In quantum field theory, every field is an infinite collection of modes, like a set of harmonic oscillators spread across space. Even in the lowest energy configuration, those oscillators retain zero-point motion. In the visuals, a flat line becomes a trembling one. The trembling is not a literal particle popping in and out like foam, yet it is not nothing either. It is encoded in correlation functions, in the way measurements at 2 points are statistically linked. Those correlations have consequences we can measure. The Casimir effect, for example, produces a tiny force between closely spaced conducting plates. It is a reminder that empty space can push back when boundaries restrict quantum modes. Third is the absence of classical spacetime, where geometry is not a fixed background. Quantum gravity proposals treat spacetime as emergent or replaceable. This rung is harder to picture because our brains are trained on geometry. General relativity makes spacetime dynamic, but it still assumes a smooth manifold. Quantum gravity asks what happens when even smoothness is not guaranteed. In some proposals, geometry is built from discrete elements, like spin networks or causal sets. In others, spacetime is a derived, approximate description of deeper degrees of freedom. The common theme is that where and when are not fundamental labels. In the visuals, the grid that once held the universe begins to pixelate, then dissolves into a web of relations. Distances stop being continuous, and the notion of a single global time becomes a convenience rather than a bedrock. Fourth is the absence of anything whatsoever, with no fields, no geometry, no states. Physics rarely reaches this rung because models need a framework. This is the rung that tempts philosophy into the room. If there are no entities and no structure, what would it even mean to assign probabilities, or to speak of possibilities? Even the word absence seems to presuppose a contrast with presence. This distinction matters because popular claims often slide between rungs without warning. A universe from nothing usually means from a vacuum, or from no classical spacetime. The slide is subtle because the word nothing is doing rhetorical work. It suggests a dramatic leap from absolute emptiness to everything we see. Yet in the technical sense, many of these stories begin with a richly defined state. Even the most radical quantum cosmology still assumes a rule for amplitudes. It assumes mathematics, consistency, and a space of possibilities. When physicists write a path integral or a wave function of the universe, they are not writing nothing. They are writing a calculus of alternatives, with weights assigned by an action or a constraint. That calculus may be profound, but it is not absence. So we ask a sharper question. Can nothing have laws, or do laws require something to be true of? The question sounds simple, but it hides a trap. If laws are statements, they seem to require a language and a logic. If laws are constraints, they seem to require a domain to constrain. One view treats laws as descriptions of regularities in the world. If nothing exists, there are no regularities to describe. This is the empiricist instinct in physics, and it is historically powerful. Newton's laws summarized patterns in motion, and Maxwell's equations summarized patterns in electricity and magnetism. In this view, laws are compressions of observed behavior. Another view treats laws as prescriptions that govern what can happen. That sounds like laws could exist without a universe, but it risks reifying equations. If laws are prescriptions, then the universe looks like a performance of a script. Yet scripts normally exist on paper or in minds or in some substrate. If there is literally nothing, where would the prescription be? Physics usually behaves as if laws are compact descriptions of patterns, yet the early universe story often talks like laws are prior, waiting to act. That shift in tone is easy to miss. We say, the laws allowed inflation, or the vacuum decayed, as if the laws were standing outside the universe. It is a useful shorthand, but it can smuggle metaphysics into a scientific sentence. Symmetry principles show why this tension is not just wordplay. Symmetries constrain what interactions are possible before any specific solution is chosen. A symmetry is a kind of invariance, a statement that some transformation changes nothing essential. Rotate an isolated system, and the underlying physics looks the same. Translate it in time, and the rules do not care which moment you call now. In the visuals, we see a sphere turning in darkness, then a set of equations staying unchanged as coordinates shift. The point is not aesthetic, it is structural. Symmetry is a way the world refuses to reveal a preferred frame. Conservation laws feel like deep necessities, but they depend on background structure. Noether's theorem ties conserved quantities to continuous symmetries. Historically, this was a revelation. Emmy Noether showed in 1918 that conservation is not a separate miracle, it is the shadow cast by symmetry when you write the dynamics in a particular mathematical form. Energy conservation is tied to time translation symmetry. If time is not fundamental or not globally defined, energy may not be a universal bookkeeper. In everyday physics, energy is the currency that never disappears. Yet in an expanding universe, even in standard cosmology, defining a global conserved energy is subtle. The redshifting of photons already hints that the familiar bookkeeping can fail. Momentum conservation is tied to space translation symmetry. If classical space is emergent, momentum may be approximate, local, or state-dependent. In curved space-time, momentum conservation is typically local rather than global, and it depends on the presence of symmetries called killing vectors. If the geometry itself is fluctuating, the very conditions that guarantee a conserved momentum may only hold in a coarse-grained limit. This is the first philosophical shadow cast by quantum gravity. If space-time is optional, then some familiar laws are emergent bookkeeping, not eternal commandments. Emergent does not mean unreal. Temperature is emergent from molecular motion, yet it is indispensable. The question is whether conservation laws are like temperature, powerful but not fundamental. The second shadow is causality. Our intuition says every event must have a cause earlier in time. That intuition is not arbitrary. It is trained by a world where memory points one way, where eggs do not unbreak, and where signals travel at finite speed. Causality is stitched into our experience of agency and explanation. But if time itself emerges, the phrase earlier in time may not apply at the deepest level. Causality can become a derived relation inside a semi-classical regime. In some quantum gravity settings, the fundamental description is not events in time. It is a constraint equation, or a network of relations from which time appears only when the universe is in a particular state. The order we call cause then effect may be a pattern that holds only after emergence. In general relativity, causality is encoded by light cones, and light cones are geometry. If geometry is quantum or undefined, causal order can blur. Light cones tell you what can influence what, because nothing outruns light. Yet if space-time fluctuates, the cone itself can fluctuate. The boundary between time-like and space-like separation can become fuzzy, at least in a regime where quantum superpositions of geometry matter. Some approaches replace causal stories with boundary conditions. Instead of a dynamical cause, you specify a condition that selects allowed histories. This sounds abstract, but it is a familiar move in physics. When you solve a differential equation, you often do not ask what caused the solution. You give initial data or boundary data, and the solution is the one that fits. A boundary condition is not an event that triggers another event. It is a constraint on the whole solution, like choosing which trajectories are permitted. In the visuals, a bundle of possible histories appears like threads. A boundary condition is a comb that allows some threads to pass and blocks others. The selection is global, not a push from one moment to the next. Quantum cosmology proposals make this explicit. No boundary and tunneling proposals are not causes, they are rules for which histories contribute. The no-boundary idea, associated with Hartle and Hawking, pictures the early universe in a way that resembles a smooth cap rather than a sharp edge. The tunneling idea, associated with Vilenkin, frames the beginning as a quantum transition. Both rely on a mathematical rule for weighting histories. Even inflation, which feels dynamical, still leans on a prior state. It needs a field, a potential, and a regime where time makes sense. Inflation is often narrated as a dramatic burst of accelerated expansion that stretches tiny regions to cosmic size. Yet to run that story, you must assume an Inflaton-like degree of freedom, a potential energy landscape, and a semi-classical space-time where expansion is well defined. So the beginning becomes less like a first domino and more like a consistency requirement. The universe is the set of histories that satisfy the constraints. In this view, the start is not a moment when nothing flips into something. It is a boundary in the space of solutions, a condition that makes the whole story hang together. The universe is what remains after consistency has done its filtering. That sounds like an evasion, but it is also how physics often works. We do not ask what causes an electron to have spin, we accept a consistent structure. Spin is not a tiny ball literally rotating, it is a quantum property tied to representation theory and symmetry. We accept it because it is coherent and predictive, not because it has a mechanical cause in time. Still, the mind pushes back. If we replace causes with boundary conditions, we have not answered why those conditions hold. The dissatisfaction is not childish, it is methodological. Science thrives on deeper unifications, and boundary conditions can feel like leftover arbitrariness. The question becomes whether the arbitrariness is temporary or permanent. This is where the chapter's tension peaks. Every explanation seems to smuggle in a framework that is already something. The camera in our mind keeps trying to zoom out. Each time we think we have reached the foundation, we find another layer. A rule, a space of states, a notion of probability. The foundation keeps behaving like a floor that recedes. Consider the claim that nothing is unstable. In quantum field theory, the vacuum can decay if it is metastable. A metastable vacuum is like a ball resting in a shallow valley, not the deepest valley available. Quantum mechanics allows tunneling, so the ball can appear on the other side of a barrier without climbing over it. In field theory, that tunneling can nucleate bubbles of a lower energy phase, but metastability is defined relative to a potential, a Hilbert space, and a time parameter for evolution. Instability only makes sense inside a rule-governed arena. You need a notion of state, a Hamiltonian or action, and a way to talk about change. Without those, the word decay has no target. It is not that the idea is wrong, it is that it belongs to rung 2 or 3. Even vacuum fluctuations require a definition of modes, and modes require geometry. The vacuum is not the 4th rung of nothing, it is the 2nd. Modes are defined by wavelengths and frequencies, and those ideas presuppose distance and time. In curved or rapidly changing spacetime, even defining particles becomes observer-dependent. The vacuum is already a sophisticated concept, not a blank. So when we say the vacuum produced the universe, we're not saying nothing produced something. We're saying one structured state transitioned to another. The transition may be extraordinary, but it's still a transition within a framework. It is like saying water froze into ice, not like saying geometry and logic appeared from absolute absence. The rhetoric of nothing can hide the real content. This reframes the central question. Are we asking for a physical mechanism within a given framework, or for the origin of the framework itself? Mechanisms are what physics does best. Frameworks are what physics usually assumes. At the beginning, the two are entangled, and separating them becomes part of the work. At this point, 3 broad interpretations compete. Each offers a different kind of stopping point, and each has a different cost. First is the universe as a brute fact. The laws and initial conditions are simply the case, with no deeper reason available. This view has a long philosophical lineage, and it can be emotionally bracing. It says there may be a point where why is not answered by deeper because. The world may just be, and our task is to map its regularities. This view is not anti-science, it is a claim about where explanation ends. It says the demand for why can outpace what the world supplies. In practice, physicists often live with brute facts temporarily. The value of the electron's mass is a brute fact until a deeper theory relates it to something else. The brute fact stance claims that, at the deepest level, the temporary may become final. The brute fact stance can still do physics aggressively. It focuses on compressing the world into the simplest consistent laws, then stops. Compression is not trivial. It is the reason a handful of equations can describe stars, semiconductors, and the early plasma. Even if the deepest why is unanswered, the how can be astonishingly complete, but it leaves a residue of dissatisfaction, because it feels like giving up. It also risks confusing no explanation with no possible explanation. The danger is psychological as much as logical. If we declare the boundary too early, we may stop searching for connections that are actually there. The line between humility and resignation is thin. Second is the universe, as a consequence of deeper mathematical consistency. The universe exists because a self-consistent structure exists, and inconsistency cannot. This view treats mathematics not as a language we invented, but as the underlying form of reality. If a structure is internally coherent, then in some sense it is. The universe is then one coherent structure among possible ones. In this view, laws are not imposed on reality, they are the structure of reality. The universe is a mathematical object, and we are patterns inside it. The appeal is that it shifts the question. Instead of asking why these laws were selected, you ask what it means for any structure to exist. The observer becomes a sub-pattern, like a knot in a tapestry that can describe the weave. This can make why something rather than nothing feel inverted. Nothing is not a stable option, because a consistent structure is already a kind of something. If consistency is unavoidable, then nothing is not the default. The default is the space of consistent possibilities, and the puzzle becomes why we inhabit this particular region. The inversion is elegant, but it is also slippery. The strength is that it avoids arbitrary choices by appealing to necessity. The weakness is that it can slide into unfalsifiable metaphysics if it predicts everything. If every consistent structure exists, then any observation can be accommodated somewhere. Prediction becomes a problem of selection, and selection can drift towards story rather than test. Physics demands more than coherence. It demands contact with measurement. Consistency alone may not pick a unique universe. Many consistent structures may exist, and then selection returns in a new disguise. Even within a single theoretical framework, there can be many solutions, many vacua, many effective low-energy laws. The landscape idea in high-energy theory is one expression of this multiplicity. The deeper the mathematics, the more room there can be. Third is anthropic reasoning and selection effects. We observe conditions compatible with observers, so some parameters may be environmentally selected. Anthropic reasoning begins with a simple statistical fact. You cannot observe a universe in which observers never form, so your data are conditional, filtered by your own existence. Cosmology uses this most often for the cosmological constant problem. A too large vacuum energy prevents galaxies, and without galaxies there are no observers. The cosmological constant sets the acceleration of cosmic expansion at late times. If it were much larger and positive, matter would thin out before it could clump into galaxies. If it were large and negative, the universe could recollapse too quickly for complex chemistry to unfold. Anthropic reasoning can be a legitimate inference about conditional probability. It is not a mechanism, and it does not replace dynamics where dynamics are testable. Used carefully, it is like correcting for a sampling bias. It tells you that certain observed values are not surprising given that you are here to observe them. It does not tell you how those values were produced. Its risk is that it can become a permission slip for any value. If a multiverse is invoked without independent evidence, prediction can dissolve into storytelling. The multiverse is not a single claim, but a family of ideas tied to inflationary dynamics or to theory landscapes. Yet without observational handles, it can become a container for everything, and therefore an explanation of nothing. The line between inference and escape hatch matters. Even with a multiverse, one must define a measure to compare regions. The measure problem can make typical ambiguous, and ambiguity weakens explanatory force. If there are infinitely many regions with different properties, you must decide how to count them. Different measures can change what is likely, sometimes dramatically. Without a principled measure, anthropic predictions can become arbitrary. These three interpretations are not mutually exclusive in practice, A model can be mechanistic locally, anthropic for some parameters, and brute at the deepest boundary. In the real workflow of cosmology, these categories often overlap. You might compute a mechanism for structure formation, treat some constants as environmental, and accept a boundary condition as given. The philosophical neatness is not guaranteed by nature. Now we bring in a clue that refuses to fit neatly into any of them. It is the arrow of time, and it points straight at the beginning. In the visuals, we see a river of events flowing one way. Broken cups do not reassemble, smoke does not unmix, and memories accumulate like sediment. The arrow is not merely psychological, it is physical. Thermodynamics says entropy tends to increase, and that increase defines a direction we call future. The universe has an arrow, and it is remarkably consistent. Entropy is often described as disorder, but in physics it is more precise. It counts the number of microscopic configurations compatible with a macroscopic description. More entropy means more ways to be the same at the level we can see, yet the microscopic laws we use are mostly time-symmetric. They do not strongly prefer a direction, so the arrow must come from boundary conditions. Classical mechanics, electromagnetism, and even quantum dynamics in their basic forms do not forbid time reversal. The asymmetry appears when you specify a special state, and then evolve away from it. The arrow is a story about initial conditions as much as laws. That boundary condition appears as a low-entropy early universe. The early cosmos was hot and dense, but also extraordinarily ordered in gravitational terms. This is the counterintuitive part. Hot and dense sounds messy, and for matter in a box it would be, but gravity changes the bookkeeping, because the highest entropy gravitational states are not smooth, they're clumped. A uniform plasma is high entropy for matter, but low entropy for gravity. Clumping increases gravitational entropy, so smoothness is a special state. As the universe expands and cools, gravity amplifies tiny density variations. Gas falls into potential wells, stars ignite and galaxies form. This clumping is not a violation of the second law. It is one of the ways entropy increases when gravity is present. In the visuals, a nearly uniform glow begins to ripple. Those ripples become filaments, and the filaments become a cosmic web. The arrow of time is visible as structure emerging from smoothness. Inflation can explain why the universe is smooth on large scales. It does not automatically explain why the total state begins in a low entropy condition. Inflation stretches space so rapidly that any initial curvature or inhomogeneity is diluted. It also provides a mechanism for generating the seeds of structure through quantum fluctuations stretched to cosmic scales. Yet the question remains, why was the inflating patch itself in the right condition? Some argue inflation is an attractor that makes low entropy generic. Others argue inflation itself requires special conditions, and the entropy puzzle remains. The debate is technical and subtle. It depends on how you define entropy in cosmology, what counts as a typical state, and which degrees of freedom you include. It also depends on whether you treat the inflaton as a special field or as an effective description. Either way, the arrow of time is not a side issue. It is a direct why this universe question, because it asks why the initial state was so constrained. If the early universe had been in a generic high-entropy gravitational configuration, it would likely have been dominated by black holes or extreme inhomogeneity. The smooth, expanding cosmos we infer from the CMB would not have emerged. The arrow points to a rare beginning. If time is emergent, the arrow becomes even stranger. We might need a notion of entropy and information that does not presuppose a global time parameter. In some quantum gravity approaches, the fundamental description is timeless, with dynamics appearing as correlations between subsystems. Then, entropy increases with time must be rephrased as certain correlations become more coarse-grained along an emergent parameter. The arrow becomes relational. Quantum information language offers hints. Entanglement structure can define effective geometry, and coarse graining can define thermodynamic behavior. Entanglement is a pattern of shared quantum information, and it can mimic spatial connectivity. In some ideas, the amount and structure of entanglement help determine what we call distance. Coarse graining, meanwhile, is how we ignore details and obtain a thermodynamic arrow, but hints are not answers. The low entropy beginning remains one of the most stubborn facts in cosmology, because it is both observed and unexplained. Observed because the CMB is astonishingly uniform and because large-scale structure grew from small, simple perturbations. Unexplained because the laws we use do not demand such a special starting point. The arrow remains a clue without a full theory. Now we tighten the loop back to laws. Conservation laws and causal stories rely on time, and the arrow of time relies on a boundary condition. When we say energy is conserved, we lean on time symmetry. When we say causes precede effects, we lean on temporal order. When we say entropy increases, we lean on a special past. The concepts support each other like beams in a structure. So the beginning is where three demands collide. We want a cause, we want laws, and we want an arrow, but each seems to require the others. If you try to ground causality in laws, you need time. If you try to ground time's direction in entropy, you need a boundary condition. If you try to ground the boundary condition in a cause, you circle back to time again. The collision is conceptual, not merely technical. This is the chapter's climax. The closer we get to nothing, the more our explanatory tools depend on assumptions that are already something. The visuals return to the ladder of absences, now lit from below. Each rung casts a shadow shaped like an equation, a symmetry, a probability rule. The shadow suggests that our tools are not neutral. They are part of the story. We can still ask what science can legitimately claim here. Science is not a mood. It is a method for comparing models under empirical constraints. Historically, cosmology matured when it became quantitative. The shift from philosophical speculation to precision measurement was driven by data, galaxy redshifts, the CMB, nucleosynthesis, and later the detailed mapping of anisotropies. The method is what gives the mystery its discipline. Operational definitions matter. If a term cannot be tied to measurements even in principle, it may not belong in physics, even if it belongs in philosophy. This does not mean physics is shallow. It means physics is careful about meaning. Time, energy, and particle are not just words. They are linked to procedures, instruments, and idealized experiments. Empirical constraints still reach surprisingly far back. The CMB power spectrum, polarization, and large-scale structure encode early universe statistics. The CMB is a photograph of the universe when it was about 380,000 years old, when electrons and protons combined and light began to travel freely. Its tiny temperature variations at the level of tens of microkelvin encode information about primordial fluctuations. Those fluctuations are the seeds from which galaxies grew. Polarization patterns add another layer. E modes trace density perturbations and scattering geometry, while B modes, if primordial, could reveal tensor perturbations linked to inflationary gravitational waves. Even non-detections constrain the energy scale of early dynamics. Primordial element abundances constrain the thermal history. Limits on non-Gaussianity constrain classes of inflationary and alternative scenarios. Big Bang nucleosynthesis predicts the relative amounts of hydrogen, helium, and lithium based on the expansion rate and the density of baryons. Observations of helium in low metallicity environments and deuterium in distant gas clouds act like a fossil record. They tell us the early universe followed a specific thermal path. Non-Gaussianity is a statistical fingerprint. Simple single-field slow-roll inflation predicts fluctuations that are close to Gaussian, with only small deviations. Larger non-Gaussian signals would point to more complex dynamics or additional fields. Future gravitational wave searches could probe phase transitions, cosmic strings, or primordial tensor modes. These signals would narrow the space of viable beginnings. Gravitational waves are messengers that travel largely unimpeded, carrying information from epochs opaque to light. A stochastic background could reveal symmetry-breaking transitions, or the dynamics of defects like cosmic strings. It could also constrain inflationary models by limiting or detecting primordial tensor power. Yet there may be a horizon of principle, not just technology. If different pre-Big Bang stories produce identical late-time observables, they may be undecidable. Two distinct theories can agree on every measurable prediction in our observable patch. If so, the difference between them is not an experimental question, but a choice of description. Physics then becomes a study of equivalence classes, not unique narratives. Undecidable does not mean meaningless, but it changes the kind of claim we can make. We might only rank models by simplicity, coherence, and fit. Simplicity here is not aesthetic minimalism. It is the preference for fewer adjustable parameters and clearer explanatory links. Coherence means internal consistency and compatibility with established physics in the regimes where it works. This is not defeat, it is intellectual hygiene. It prevents us from mistaking a preferred narrative for a measured fact. Cosmology has learned this lesson repeatedly. Elegant ideas have fallen when data arrived, and messy models have survived because they matched observations. Hygiene is what keeps mystery from turning into mythology. So where does that leave the central question? What does physics mean by nothing? And can it answer what could exist before the Big Bang? The word before is itself a test. If time begins, before may be like north of the North Pole. Yet physics can still ask what conditions replace the classical notion of earlier times, and what signatures those conditions might leave. Physics answers best on rungs 1 through 3. It can model empty space, quantum vacuum, and even regimes without classical spacetime, using proposed quantum rules. On rung 1, we have classical and semi-classical field theory, with well-defined geometry. On rung 2, we have quantum fields, renormalization, and vacuum structure. On rung 3, we have candidate frameworks, still incomplete, where geometry is emergent or quantized, and classical spacetime is a limit. Physics struggles to address rung 4, absolute nothingness, because a model without any framework cannot be written, tested, or even clearly stated. To write a model, you need a mathematical language. To test it, you need observables, even if indirect. To state it, you need logic and consistency. Absolute nothingness threatens to remove the very tools required to speak. That may mean the question is misasked. We may be demanding an explanation that presupposes time, laws, and logic, then asking for their origin. It is like asking for a map of the place where maps cannot exist. The demand is understandable, but it may be category confused. The beginning might not be an event inside time, and laws might not be objects that float free of reality. Or it may mean the question points to a new kind of answer. The origin might be a consistency condition, a boundary principle, or an informational constraint. These are not magical phrases. They're attempts to replace cause with selection, and to replace earlier with allowed. They keep the discussion within the discipline of physics, even as they stretch its usual intuitions. Either way, the universe does not leave us with pure silence. It leaves patterns, and those patterns are the reason this mystery is scientific at all. Patterns are what survive the abyss. They're encoded in spectra, correlations, and distributions across the sky. Even if the deepest rung remains unreachable, the higher rungs still constrain what can be true. We return from abstraction to the sky. Whatever the beginning was, it had consequences, and those consequences are still written in photons and structure. In the visuals, the CMB fills the screen like a mottled ancient parchment. Galaxies trace filaments like faint threads of light, and clusters glow in X-rays where hot gas pools in deep gravitational wells. The universe is not only a question, it is a record. In the final chapter, we test origin stories against what the universe actually lets us see. The limits of explanation become a map for the next measurements. The mystery remains, but it is a discipline mystery. Each new survey, each improved detector, and each refined statistical test narrows the space of beginnings. The question of nothing stays with us, because the sky keeps answering in the only language it has. We end where the earlier chapters kept pointing, at a boundary, not a blank, and not a simple wall. The Big Bang is the earliest well-tested chapter of our map, and the question is how close evidence can push us. In practice, that means asking what survives the heat, the expansion, and the loss of direct memory. Chapter 1 warned that before can smuggle in a background clock, as if time were a container waiting to be filled. Chapters 2 and 3 showed that nothing is already structured if space-time and fields exist, because laws and degrees of freedom are not emptiness. Chapters 5 and 6 tightened the dilemma. Quantum gravity may erase the stage, and explanation may become boundary conditions instead of causes. In other words, the deepest account might look less like a story and more like a specification. So the final task is practical. What observations can distinguish inflation, bounces, and other pre-hot Big Bang scenarios without pretending imagination is data? What can be measured, what can only be inferred, and what might be permanently hidden by the limits of our horizon? Evidence about the earliest universe is mostly statistical, because the early cosmos did not leave us a diary. We cannot watch the beginning directly, but we can test the fingerprints it would leave on later patterns. Those patterns are not arbitrary decorations. They are the frozen record of quantum fluctuations stretched to cosmic scales. The cosmic microwave background remains the cleanest canvas because it comes from a time when the universe first became transparent. It is not only a temperature map, it is a probability distribution written across the sky. When we look at that mottled afterglow, we are seeing a snapshot of density and velocity variations at recombination, imprinted when electrons finally bound to protons. Visually, the CMB is a sphere of faintly speckled light, hotter and colder by mere tens of microkelvin. Yet those tiny differences encode a competition between gravity pulling matter in and radiation pressure pushing it out. The resulting acoustic peaks in the power spectrum are the harmonic notes of the early plasma, and they tell us the universe was once a resonant instrument. Start with polarization, because it separates kinds of primordial motion and reveals geometry in a way temperature cannot. Thomson scattering turns local quadrupoles into polarization, and the pattern decomposes into E modes and B modes. The decomposition is mathematical, but the intuition is simple. E modes look like gradients, while B modes look like curls. E modes are already a precision tool, and their detection is one of modern cosmology's quiet triumphs. They sharpen parameter estimates, confirm acoustic physics, and help isolate subtle signatures that temperature alone can hide. Because polarization responds to velocity and local anisotropy, it cross-checks the same early physics with a different lever arm. In the visuals, E modes appear as delicate aligned whiskers across the sky, coherent over degree scales. Their correlations with temperature peaks and troughs are not just pretty symmetry, they are a timing measurement. That phase relationship tells us the perturbations were coherent, as expected from simple inflationary initial conditions. B modes are the prize and the trap, because they can arise from multiple sources that overlap on the same sky. Primordial tensor waves generate a distinctive curl pattern, while gravitational lensing and dust can mimic parts of that signal. The challenge is that the universe is generous with curls even when the origin is mundane. Primordial B modes, if they exist at detectable levels, would be the imprint of gravitational waves from the earliest moments we can probe. These waves would stretch and squeeze space-time itself, and then leave behind a twisting polarization pattern at large angular scales. It is a remarkable idea that quantum fluctuations of the metric could become a map you can plot. Foregrounds are not an annoyance, they are a competing universe layered on top of the one we want. Galactic dust and synchrotron emission have their own polarization spectra, and they must be modelled across frequencies to avoid false discovery. Dust grains align with magnetic fields, and that alignment turns the Milky Way into a polarized screen. The visual reality is humbling. The clean cosmological signal is faint, while the galaxy is bright and structured. At some frequencies, the sky looks like smoky filaments, and at others it looks like a web of magnetic turbulence. The only way through is redundancy, many frequency bands, careful component separation, and constant skepticism. Lensing B modes are both contaminant and resource, because the same effect that blurs the early sky also teaches us about later structure. Delensing can remove them to uncover primordial power, and the lensing map itself constrains structure growth and neutrino mass. Lensing takes E modes and remixes them into B modes, as intervening matter bends photon paths. Delensing is not a single trick, it is an entire strategy of inference. One builds a map of the projected gravitational potential using the CMB itself, or using galaxies and their shapes, and then subtracts the expected lensing contribution. The better we map the cosmic web, the more we can unmask what is truly primordial. If primordial B modes are detected, the implication is immediate and unusually direct. The tensor-to-scalar ratio would fix the amplitude of primordial gravitational waves and point to the energy scale of inflation-like dynamics. In simple models, that scale can be related to the height of the potential driving accelerated expansion. That measurement would not automatically prove a specific inflaton potential, and it would not close the case on microphysics. It would instead bound classes of models, because different mechanisms can generate tensors with different tilts and consistency relations. Even within inflation, the same tensor amplitude can arise from different field ranges and different kinetic structures. A detection would also force a careful consistency check across observables. The tensor tilt, the scalar tilt, and the reheating history would have to fit together without hidden tuning. The universe would be telling us not only that a mechanism worked, but that it worked in a tightly constrained way. If B modes remain undetected, that is still decisive, because absence becomes a measured constraint. It pushes inflation toward lower energy scales, disfavors large field models, and strengthens alternatives that predict tiny tensors, it also sharpens the question of naturalness. Why would the early dynamics produce scalars but almost no tensors? Next is the scalar spectrum because it encodes the engine that made structure and seeded everything that later formed. The spectral tilt NES already tells us the perturbations are nearly scale invariant, but not perfectly so. That slight redness, more power on large scales, acts like a fingerprint of slowly changing dynamics. Historically, this was one of inflation's early successes, because scale invariance was not an obvious prediction of older ideas. A nearly scale invariant spectrum also echoes an aesthetic of critical phenomena, where systems lose memory of microscopic details. Yet the deviation from exact scale invariance is where the physics lives, because it measures the departure from perfect symmetry. Running of the tilt tests whether the early dynamics were smooth or featured, as if the inflating field rolled down a perfectly gentle slope. A significant running would hint at departures from slow roll, multiple fields, or pre-inflationary evolution. It could also signal a brief interruption, an event in the potential that left a ripple in the spectrum. Features matter because they are one of the few ways a pre-hot Big Bang phase could announce itself. A bounce, a fast roll stage, or a transition into inflation could imprint oscillations or cutoffs at the largest scales. The difficulty is that cosmic variance limits our certainty on those scales, because we only have one sky. Non-Gaussianity is the sharpest statistical discriminator we have, because it probes interactions rather than just initial amplitudes. Simple single-field slow-roll inflation predicts nearly Gaussian fluctuations, while extra fields, non-canonical kinetics, or alternatives can amplify higher point correlations. In plain terms, Gaussianity means the map is fully described by its two-point statistics, and anything beyond that is new information. The bispectrum is not one number, it is a shape, and the shape tells you what kind of physics coupled the modes. Local, equilateral, and orthogonal templates correspond to different physical mechanisms, and large-scale structure can measure them differently than the CMB. A local shape often points to multifield dynamics, where one field modulates another after horizon exit. Equilateral-type signals, by contrast, tend to arise when the inflaton has non-standard kinetic terms and a reduced sound speed. That changes how fluctuations propagate, and it increases interactions at horizon crossing. The language is technical, but the idea is intuitive. Stronger interactions leave stronger statistical fingerprints. Isocurvature modes are another fork in the road, because they represent a different kind of initial condition. If initial perturbations include relative fluctuations between components, they point to multi-field dynamics, or specific dark matter production histories. Instead of all components rising and falling together, one component can fluctuate against another, like a chemical mixture separating. Constraints on isocurvature are already stringent, which is itself a clue about the simplicity of the early universe. Yet even a small detected fraction would be profound, because it would identify additional degrees of freedom active at the beginning. It would also connect cosmology to particle models that naturally produce such modes, including axion-like fields. Now widen the window beyond photons. Primordial gravitational waves are not only a CMB target, because the early universe can produce backgrounds across many frequencies. The sky is not just a picture, it is also a soundtrack spread across decades of wavelength. A stochastic gravitational wave background would act like a new fossil record, because gravitational waves travel almost unimpeded once produced. It could encode inflationary tensors, but it could also encode phase transitions, cosmic strings, or other high-energy relics. The hard part is that multiple cosmic processes can sing in overlapping bands. The key is to separate primordial backgrounds from astrophysical foregrounds, because the universe is full of late-time noise. Compact binaries create a confusion background, and careful spectral and anisotropy analyses are needed to isolate a cosmological component. The separation is statistical, relying on how signals scale with frequency and how they vary across the sky. Different detectors listen to different epochs, and that division is one of our strengths. CMB polarization probes ultra-low frequencies tied to horizon-scale tensors, while pulsar timing arrays, space interferometers, and ground detectors probe later, higher frequency sources. Together they form a multi-band observatory